Tamam Devran, girebildim sonunda. Devran, beni duyuyor musun?
Hocam her şey...
Efendim? Ayşegül merhaba.
Good morning. Merhaba hocam. Everybody is hearing us right now, I think. Good morning, everyone. We are just arranging who's the panelist and who's the attendee right now. So welcome. And we'll start our welcome talks soon.
Good morning everyone from Istanbul also. Devran, şey yaptın mı? Panelist ya da host yaptın mı Ayşegül'ü?
Tabii hocam. Ayşegül Hoca.
Tamam. Şimdi Munip'te
şeyimiz akıyor hocam.
Tamam. Munip'te ilk toplantı yapan kişileri de panelist yapalım. Tamam mı?
Tamam hocam, şimdi yapıyoruz.
Kızlarımız da burada. Devran, onları şimdi 15-17 arasında şey var. Yük denetimi var biliyorsun. Bu araştırma görevlilerinin hepsinin bulunması gerekmiyor. Sen onları ayarlarsın, oldu mu?
Tamam hocam. Ben buradayım, meraklanmayın.
Tamam. Ayşegül, ne zaman istersen başlatabilirsin açılışı.
Tamam. Panelistleri ayarlayalım, başlatalım.
Katılımları bir göreyim, bir bakayım. 32 kişi var şu anda.
Morning.
Hi.
How are you?
Good morning, Inma. How are you?
Fine. Good morning, everyone.
¿Cómo estás?
Bien, bien. Estoy bien. Nice to meet you.
Nice to meet you also.
Nice to meet you too.
Hey, Munib. Hello.
Good morning.
Good morning. ¿Cómo está tu madre ahora, Inma?
Está un poco mejor, todavía débil, pero un poco mejor.
Muy bueno.
Y está en casa, que es importante.
Munib, your microphone is off.
Munib, your micro.
Estoy muy contento de escuchar esto.
Now it's okay.
Now it's okay. Welcome.
Yes. So wonderful. So there will be an adventure this week.
Yeah.
You have made that great work, actually. Amazing.
Amazing.
Congratulations.
Yeah.
Congratulations.
Thank you. With you all.
Yeah, Orhan and Azarquiel, they're good. And Inma in the background.
Thank you very much for you and all the board members.
So this is good work.
Yes, we are sure that a very useful meeting will take place.
A little bit overload. Oh my God. I mean, amazing how many topics you have.
Yes, and we have 30 student presentation, no? At least, I think.
It's enormous, actually. So, but this is, well, fine. Let's see what happens.
It's a pity we are not in person together.
Yeah.
Yes,
So
such a pity. We are in difficult
Istanbul,
times.
Beirut, Granada, yeah.
Yeah, that's what the West and East.
but it's difficult time, so it's perfect now in this way.
Yeah. Again. So let's say I hope it will work very good. Have a lot of audience and so, and we'll do our best. So how many participants are there?
Well, actually, we have 104. Four of them actually defined that they will not be able to attend. So we have 100 participants. I am Just worried that they didn't get the Zoom link. Some did not, but we will fix that in meanwhile.
So the major number is from how many from Europe, let's say?
Well, I didn't divide into continents, but we have around 16 from Turkey, another 16 from Egypt. Those are the major attendees, maybe a 10 from Italy and also Spain. And we have some from Bulgaria and 33 different countries, actually.
From the Arab countries also?
Also, yes.
I see.
We have even from Madagascar, Zambia, United States,
Wow.
and a great variety of
Morocco, Algeria, no, Nepal, yes, a lot of countries.
Yes, we have a great variety of participants from all over the world.
I didn't say participants for Lebanon.
Yeah. Well, I mean, Lebanon is in bad shape. Anyway, so this is actually the world is connected by this technology. So it's impossible to have so many people at one time in a conference or so. It's just a matter of how do you want to pay it and so on. This online, the Zoom issue session is wonderful.
Spain 10, Egypt 10, Italy 11.
Yeah. So you
And
should,
Turkey, yes.
that's very nice. So where are the other people now attending? I do not see many of the students.
Yeah, we have 26 attendees right now and 10 panelists. Some of them are from Aydın University, giving us some technical support.
Panelists and attender 46.
36 at the moment, right?
I have a question concerning my talk.
Yes.
My lectures. Can I make a break after the first?
Sure. Yes.
About 5 minutes or how long?
That's up to you. Maybe 5 or 10. If you make a bigger break, then they might lose attention.
Because I changed the subject. So
yeah, you're right. Of course, I mean, every lecturer has this right.
Okay, so
make a short
these are
break in
50
between.
minutes, right?
Sorry?
One.
Which one
50
is?
minutes each one, each lecture.
50 minutes, yes.
Yeah, okay, fine.
Including question, including question.
Including the questions.
So and
you can keep it 40 minutes and 5 minutes, maybe questions or 10 minutes.
It depends.
Yeah, well, you're flexible in that area.
Okay, so
it's your lecture.
So my lecture starts here at my time is 9:30.
Yeah, your time, yes.
Because
about
we have
in 15,
1 hour before.
15 minutes later from now.
Okay. So
shall we wait a little bit more, or should we start welcoming?
Let's wait 3 minutes.
Okay.
15 at 15 we.
Ayşegül hocam, chatinize baksanız.
Evet. Hocam bunları da mı YouTube'dan veriyoruz biz şimdi?
Evet hocam.
Ona gerek var mı?
Yok, gerek yok.
Ben durdururum onu, önemli değil hocam.
Tamam.
Ha, durdur onu, durdur.
Çünkü o zaman şeye giriyoruz. KVK kanunu kapsamında falan filan.
I have a research center meeting also this hour.
Seeing that Carlos has some problem. I read in the chat.
Yeah, maybe he should reset or relaunch Zoom. Sometimes my computer does, I just reboot.
But he's in need, so he's connecting from there.
From a different maybe computer.
So I just
Her el kaldırın aldırmayalım.
I just click on my lecture and will be shared, right?
Yeah. You see on the bottom, there's a share screen button with a green icon.
Yeah, share screen.
Yeah,
Okay.
you're gonna click that one, then choose PowerPoint or whatever you're using.
Yeah, I share screen and then select my lecture.
Yeah, we will be able to see that.
Okay.
You chat with panelists only, Inma.
Okay.
So
Thank
you should switch to everyone.
Thank you.
Maurizio and Cynthia also joined us right now. Changing status to panelist. Carlos changing status to panelist. I hope you can join now.
Carlos also. Hola, Carlos.
Hello, can you hear
Hi
me?
there. Yes, we can hear you. Welcome.
Okay,
Welcome.
nice to see you again. How are you?
Nice.
I cannot activate my video. I don't know why.
It's okay for now. Maybe later it changes. It's good to hear your voice anyway. And Maurizio can...
Maurizio, where is he? Oscar. Oscar, where is
Fine.
Oscar?
no.
Oh,
Oh, now it's working.
Mauricio.
Great.
Hi.
Mauricio's here as well.
Hi, Carlos.
No, finally, thank you.
okay.
Ciao, Mauricio. Buongiorno.
He's also working on his camera, I think.
Yeah, maybe they thought that we start at 8:30 the other day. Maybe they didn't realize it was 8 today.
It's a big challenge to, organize with such a time difference for everyone.
Yeah, that's
But
right.
I think we'll make it. Everyone will get used
we
to
are
it.
not so far. We are not so far.
Yeah.
Spain, Italy.
Some people are, but
The Philippines,
they'll
I
get used to
think
it.
from the Philippines,
Yeah,
someone
yeah,
said,
even-
good afternoon. I will ask Oscar.
So, Isangul, thank you very much for your work and to Orhan too. You have did a great job this day.
Sí. Lot.
Thank you as well.
Lot of work.
As an endless support from the board. Okay, let me start some welcoming that. We already did.
Okay, thank you very much.
Oh, Maurizio. Yeah.
Yeah, but I don't think his microphone is working right now. But maybe he's hearing us. Oscar also joined right now.
Here is Oscar. Ciao, Oscar.
Oscar. Hi, Oscar.
Okay, recording in progress. Dear everyone, this is Ayşegül from Istanbul. I'll be speaking on behalf of the organizing committee. We are honored and pleased to welcome you at the 5th Azarquiel School of Astronomy, which will be held online this whole week. This school is devoted to promote cultural exchange and bringing the gap between East and West. And we will give some special attention to historical contributions of Arabs to astronomy and science, since Azarquiel was one of them. So the school is named in honor to Azarquiel. He was one of the most famous Andalus astronomers. The first school was held in Granada, Spain in 2010, hosted by INMA. And then the second school was in Lebanon in 2011, hosted by Munib. And the third school was organized in Istanbul. We hosted in Istanbul Kültür University. Then the fourth school was in Syracuse, hosted by Maurizio, one of the members of the board as well. But everything started in 2006. Maybe Inma will share a few words about that. They just had this wonderful idea to found a school for university students, PhD students, and young researchers with special emphasis to participants from Arab countries as an indication that science can unify nations and promote peace, even in periods of difficulties. And here we are in a time of isolation, such a difficulty. And we will be together during 1 week, and we will have experts with international reputation in their field of research. They are going to teach us several courses starting from today. And we will also have some public talks related to the history of science. And we're going to stream those on YouTube. And let me give you some numbers about the participants. We have 100 participants from 33 different countries, and they were encouraged to present talks for the afternoon session. So we're going to host 28 student presentations during this week. And I would like to thank our board members for their endless effort in keeping this school alive, no matter what. And I would also like to thank our sponsors, Turkish Astronomical Society and Aydın University, for being the online host. Now let me pass the word to Orhan Gölbaşı from Aydın University, another key player in the organization of this very school. Orhan Hocam.
Ses hocam.
Orhan, the microphone, we cannot listen. Okay.
I have another meetings, research centers meetings. I interested also this meeting, not to see more words. Thank you again, many thank you again for members and participants. Ayşegül, you can continue.
Okay, thanks a lot.
Yes.
And maybe some members of our board, Inma, as a starting guide for the school. You have so much work in this. Would you share a little bit?
Okay. It's a great pleasure for me to be here now at this Azarquiel school. I am from the University of Granada in Spain, as Ayşegül has told you. And I would like to thank and offer my congratulations to Ayşegül and Orhan and for the organization of this Azarquiel school. And of course to the sponsor, the Aydın University and the Turkish Astronomical Society. And I would like to extend my welcome and congratulations to all participants for being here. And I wish you a good week and a good school. I don't know, Munib, Oscar, would you like to say something?
Yeah, this is, I would just extend my congratulations for the organizations in this difficult period that we are all of us we are living. And now I'm really waiting for see what we have prepared for this meeting this year. And so I'm really want to hear the lectures and the presentation by students and the discussion that will follow, and everything that we already know from previous schools. And so I want to conclude by welcome all of you, all of you, and so that's all. Thank you.
Thank you, Oscar, Munib, and Inma. Carlos?
Yeah, well, I mean, actually, the school is wonderful. The organizer have done great work. And the school has actually this bridge of culture between West and East. This is unique, in fact. And you said the 33 nations. This is really very hard to collect these kind of people. So the school has really a tremendous impact on young people, I guess. So therefore, it should continue somehow. Okay.
I think you're right, yes. As for me, I was one of the students in the first school. Then I became, then during my career, I also became part of this school. So it was such a big step for my astronomical career, I must say that. So I think this will also change many people's lives. I mean, this was, for me, I was also interested in astronomical history of science. So it is an opportunity to combine both, actually, and meet many people.
Right.
And we are going to continue our relations from now on. I hope so. So I just sent another chat. If you haven't joined our Slack channel yet, you can join from this link in the chat. Please don't share with everyone, but participants of this school. We're just trying to check if you're a participant as well. And we will continue writing from the Slack, also from the chat, and we will start right now at, for me it's 10:30, so it's 7:30 Universal Time. We should be starting our lectures right now. Are we ready?
Yes, share the screen.
Okay.
I share the screen, right?
Okay, yes, you can now. Thank you. So we will have some social time meanwhile, and after Munip finishes his first lecture about the nucleosynthesis.
Yeah, can you see it?
No, not right now.
No.
You click the share screen button, then you choose which window to share.
Okay.
Okay.
Go.
Nope.
Now?
Nope.
Not yet?
No.
What can I do? Share screen. Host disabled. Screen
Disabled. Okay, Devran. Hocam şey yapamıyor.
Say okay.
Paylaşamıyor.
I say okay. Host disabled.
Okay, we'll change that.
Devran. Devran. Munip'i host yapar mısın?
Bir şey share edemiyor, daha doğrusu share açarsanız.
I get a message host disabled.
Okay, we'll change that. My name was. Okay, you're a co-host now. You can start sharing. Please try again.
Yes.
Yep, it's
Okay.
working right now.
Okay, so.
Okay, so our first lecture starts with Professor Munip at 8 from the American University of Beirut, and he's one of our oldest board members.
Yes.
Now it's your turn.
So actually, I was thinking about how to do these lectures, so I will not discuss the stellar models and nucleosynthesis in details. I just wanted to emphasize the basics, physical basis of stellar physics and nucleosynthesis. So I hope I can go through, and this was my motivation actually. Okay, so let's go. This is a wonderful picture of NGC 3603 taken by this very large telescope in Chile. These are 1,000 stars, 20,000 light years away, 10 million years old. So this actually tells you that the universe is written in kind of cosmic code, and it's for us to get a little of it. Okay, so this is as motivation. So okay, so the aim is to introducing the basic concept. No time to go into details. Okay. And this will make maybe animation for many students or listeners to follow up some ideas I want to present. So let's start. Why we study stars? Because they are most common cosmic objects. And they are actually constituents of galaxies. And they produce the bulk of elements and isotopes. And we humans are partly made of these chemical elements, which have been produced in stars of different generations. And therefore, we're having this, our cosmic connection heritage, okay, through the stars. And so the understanding of chemical elements in stars is a powerful tool to get more insight in their internal structure and evolution, And this allows to study the evolution of galaxies and the universe. Okay, now let me introduce in a simple way the playground of stellar evolution, the Hertzsprung-Russell diagram, which I abbreviate by HRD. So actually, the stars observed the two properties. These are the apparent brightness, you use the telescope, and you have also the tool of the color index, which is using the filter UV and V filters, is called photometry. So if we know the distance, then the inverse square law of radiation allows us to write the luminosity, that is the power of the star, which is then the area, the spherical, the area of the sphere, star is a sphere, times B, which B is the brightness. So now we have actually two versions of, let's say, HRD. One is the UV photometry, as I said, and there's the theoretical HRD, which is connects the luminosity with the effective temperature, which is related to the black body distribution. So now we should remember that most densely populated regions are found where the stars spend most of the lifetime. So the longest is on the main sequence, about 90% of the life of a star. The position and of a star in the HRD reveals at least its radius, age, and evolutionary states. Okay. So now the theoretical HRD use quantities related to stellar models. One is the Bosman, Stefan Bosman law, giving you the flux in watt per square meter is sigma radiation constant times T to the 4. And the radiant flux, which leaves the surface of a spherical object of radius r, is given by r divided by the area, 4 pi r squared. If the object can be described by a black body, this is the case, fortunately, at least approximately, and we have the radius and the temperature, then we can relate sigma T to the 4, and we equate to L over 4 pi r squared. And now, how do we use this equation to get for the star to get L? Okay, so we define the effective temperature for the photosphere of the star, which is resembled by a black body, and this is a good approximation. And we have the famous equation. The luminosity is the area times sigma T effective to the 4. Okay, here is two examples of the HR diagram. And you see here on the left side is the main sequence, the giant, the supergiant. They are classified. Here is the main sequence and giant, supergiant, white dwarf. And then you see actually here the region of these stars with the radius. So this is one solar radius, and this is 100 times, and so you supergiant because of the large radius. So actually the slope here is 4 because the effective temperature increases to the left, therefore you have this inclination to the left side. Okay, so now let's go to the basic equations. I try to get through. Okay, first of all, let's talk about hydrostatic equilibrium. Okay, here you see actually, you see that we have the Newton's second law, assuming spherical symmetry. Let's neglect rotation because that makes a complicated issue. And this is slowly contracting. The gravitational force acting on a mass element, which is shown in blue here, with the area dA and dm, the mass. And so you see here the radius r and pressure P, and then you go by dr. So you actually, the mass element dm is given by rho times the volume dv. So then you have a gravitational force. It's a minus sign here is because indicates that the direction of the force is inward. Okay, and so we have the continuity equation. The continuity equation is actually describe the mass inside this radius r, in differential form is dmr over dt, dr is 4 pi r squared times the density. Okay, so and then actually the pressure force here is we're talking about hydrostatic equilibrium. Look, I just show you the fish here. The fish is swimming at a certain level in the sea, and then you see that there's a balance of, so the net force is 0 because the pressure is higher in the bottom, inside to the center, toward the center, and there's the weight of fish and also the pressure from above. So if you use Newton's second law, this is density times acceleration, and then you have this simple formula, you know. And then finally, when you use the continuity equation, you end up with momentum equation, which is the acceleration is 4 pi r squared dB mr minus gmr over r squared, where this is gmr over r squared is the local gravity. Okay, so this is the point is the hydrostatic equilibrium. We neglect that the acceleration is 0. Actually, if you calculate the Stern model, actually the acceleration is very small. Okay, so then we have the hydrostatic equilibrium, which is actually in two versions of them. This is either related to MR or to the DR. Okay, so and then you see in general you have the nabla B minus rho delta V, where V is the gravitational potential, and this is the Bosman equation for the gravitational phi. So interesting actually here that this equation here tells you the mass appears as independent variable, and while R is a function of MR. And this the advantage is that the mass is usually constant, while the radius is to be determined. And this is the Lagrangian scheme in stellar evolution. Okay, you're moving with the mass, actually, inward or outward. So what do we learn from this hydrostatic equilibrium? Actually, we can estimate the central pressure of a star, and we also have access to the free full time scale. And I have written this in the appendix, and so I can send you the lecture separately, because I have no time to go into this kind of derivation. And we can also look at the Eddington luminosity. This is appendix 2, and we have also the so-called the virial theorem and application, which is in appendix 3. So now let's say let's estimate the pressure of the star inside the star with using the hydrostatic equilibrium. So if you take this equation, ddrb plus gmr over 8 pi r to the 4, then you can simply calculate this very easily, and you have this expression. It turns out that you use the equation above, equation 1. So they cancel, the two terms cancel, and you end up with this expression, which is negative. So the term in the bracket here decreases with the increasing r, greater at the center, where this bracket is equal to BC. Okay, and then you see actually if you equate this here in a bracket, then you have BC is larger than gm squared over 8 pi r squared, which is turns out to be 4 10 to the 14 m over m sun squared times r over r r sun over r to the power 4, and this is in dyne base square centimeter. Actually, the conclusion here, demanding hydrostatic equilibrium sets the order of magnitude of the physical variable like the pressure. So the detailed calculation for model of the sun is actually higher, is 10 to the 17 roughly. And this is far from the estimated value, since the pressure is the increasing toward the center, and this has been neglected in this kind of derivation. But however, you have actually the order of magnitude using the hydrostatic equilibrium. Now, here is the Lane effect. Is the stars to exist, they must have high pressure and must be hot systems. And here is the sun, and you see the temperature, you see the density, you see the luminosity, which is concentrated about 25% of the radius due to the hydrogen fusion to helium, and otherwise it's really constant. So the sun is a compact star in the center and diluted outside. As you see the density, or you see it's also the mass is involved here. About 35% of the mass is involved in the production of the power of the sun. Okay, free full time scale derived in the appendix. It's actually, you see the pressure is neglected completely, and therefore you have free fall definition of the time scale. And this turns out to be 1/6 to the 3 times m over m sun to the power minus 1/2 times r over r sun to the power 3/2. So the sun has, if the sun would not have any pressure, say, okay, it will live only 27 minutes. And this is amazing. So the red giant actually has a large radius. The giants have 100 of the sun, of the radius of the sun, and it has 18 days for one solar mass. So what do we learn here? We learn that the sun cannot live so long without achieving hydrostatic equilibrium. We would not be in this universe. Okay. So, and now let's go to proceed to the energy equation and the energy conservation. So I have here the center, the radius r plus dr, and I have a region where I assume that there is nuclear power here, energy production due to thermonuclear reactions. So the LR is the luminosity of the power passing through the sphere of radius r. And now we have at R0 is LR0, at R equal to the radius, the L is the L of the star itself, the luminosity of the star. So in between, L is complicated function resulting from energy transport by radiation, convection, or even conduction for later stages. So the point is that the epsilon n is the energy released per unit mass per second, or it's erg per gram in second, due to the thermonuclear reactions which are occurring in the star. So if we take the difference, LR plus DLR minus LR, we have this equal to this defines actually epsilon n multiplied by rho times the volume. So if we take the derivative of this, then you get actually simply DLR over DMR is equal to epsilon n, where we have used the continuity equation as I have introduced before. So the thermal equilibrium makes possible for the nuclear luminosity to appear at the surface of the star, because you cannot produce energy, nuclear energy inside in any location in the star without transporting it by radiation or by convection. This is happening in the sun, of course, radiation in the inner region and convection in the outer envelope. Now, here is the, we have to generalize this equation, of course, because taking the time dependence and also considering the neutrino energy losses, which appears in the late evolution starting with carbon burning, for example. And then you see here, actually, the terms with the that derivative is, this is the gravitational energy. This is the internal energy time, and this is P over rho squared dr dt. So the electromagnetic interaction, strong interaction, and weak interaction are involved in this equation. So it turns out that this difference between nuclear energy and neutrino losses play an important role in the evolution of massive stars starting carbon burning. So we have discovered the role of gravity previously, talking about hydrostatic equilibrium, and therefore the star exists because of the coordinated effort of 4 natural forces. There will be no star if omitting one of them. We will not be in this universe. Okay, Kelvin Helmholtz is also introduced, and this is derived in the appendix also. This is now tau, or tau, the English say, KH for Kelvin Helmholtz. Actually, this is the gravitational energy over the luminosity. And then you can really exact by using roughly for gravitational energy, it's not exactly factor 1/2. It's for a spherical body is 3/5, but just approximately this is then the order of 10 to the 7 times the combination of mass and radius and luminosity. So it's clear that the sun would not live about 30 million years from its own gravity reservoir. It is then clear that other long-lasting source must be operating in the sun, and of course in all stars, and this is the thermonuclear sources. But the Kelvin Helmholtz side scale is actually what's the time from the start to evolve from the main sequence to the red giant stage. Okay, here is the as a function of mass. This is the for the main sequence stars you have actually from observation you have the luminosity is proportional to m to the power 3/5. So if you take this for near 1 solar mass, then you have the proportionality is T effective to the power 8. And using the Stefan-Boltzmann law, we can extract, as you see when you have more time, the R is proportional L to the power 1/4. Using this relation L proportionality Lm to the power 3/2, you get actually 3.7 m/m sun to the power -2.4 in years, and you see that actually the consequences of this Kelvin Helmholtz time scale is that the protostar collapses to the main sequence, and the main sequence stars evolve to the red giant. So then you have actually, you see here 10 to the 8 for 0.5, for 5 solar masses, just 6 10 to the 5 years. So this is very sensitive actually to the mass. Okay. Now here is a Brownian sequence evolution, and this is the evolution after the main sequence. And you see here, if you want to go into details of this calculation, here is one of the paper. Just I'm selecting it, or 2 papers here, and you see that actually the stars evolve. This is the red giant branch, and they loop back and forth and so on. This everything is actually explained in these papers here. And here you see the different evolution to the main sequence depending on the structure of the star and depending on the mass. Okay. So now then the next one is the nuclear time scale. The nuclear time scale is actually due to the Einstein relation. This is the mc squared or delta m times c squared of the luminosity. So the hydrogen fusion, this is 4 hydrogen to protons to helium. And then if you calculate the delta m, then you have actually this difference here, which is in atomic mass units. The atomic mass units is defined by 931.5 mega electron volt per c squared. Okay, this is roughly 1/12 the mass of a carbon, neutral carbon atom. And then you see actually delta M is 0.0071 mass units per nucleon. And this number is one fundamental number in the whole universe, because every star formed in the universe has to go through this hydrogen burn. And then you calculate the nuclear energy, you calculate the nuclear time scale is then 10 to the 11 m over m sun, L over L sun to the power -1. And they see if you are talking about 10 to the 10 years, then you have actually only 0.1 of the mass involved in order to get this. So that gives you a feeling about what the sun is doing actually. Okay. So the nuclear time scale is, of course, now we have now arrived at the conclusion that the free-fall time scale is much less than the Kelvin Helmholtz, and the Kelvin Helmholtz much smaller than the nuclear time scale. And this is incredible creation. Okay. Right. هلا radiative transport. How much time I have? 30, 20, 25. Okay, fine.
Well, it's 55 minutes past, so you have still time.
Okay. I have used 25 or what? A little
You
bit
have
less.
20 minutes if you want to give a break.
Yeah. Okay. Fine. Let's see. Let's be so. If I didn't done finish this one, I proceed to the next one. So okay. So radiative energy transport. Radiation escapes from the surface of the star, and this is actually done by effective energy transport, which needs a temperature gradient in the star. Okay, so the temperature gradient existing in the star means that there is a gradient of radiation pressure as well, and this leads to the net movement of photons toward the surface of the star, and therefore we're talking about radiative flux, F with the sub-index rad, and therefore this the whole process is described by the equation when you take the radiation pressure function of R, the derivative of it is kappa is the mean opacity density over C times F rad, which I have introduced. Kappa is the mean absorption coefficient, the opacity. All atomic physics is involved in this capacity. Okay. So we talk about a beam of photon traveling to the surface. Also, photons suffer a lot until they reach the surface. So they are diffusing out from the internal region, and this is called random motion. They are dancing out. They have to interact with the atoms in the star, and therefore cannot just move through like neutrinos. Neutrinos go through in seconds. But radiation needs eventually 70,000 years for a photon to get from the internal sun to the surface. And now the thermal equilibrium is established in the stellar interior, so that we have the Planck distribution. This is the 8 to the 4th for the radiation pressure, and now we take the derivative and equating derivative to the equation before. And then you see it follows that if you introduce F rad L over R, LR over 4 pi R squared, then you end up with the actually transport equation in case of diffusion of radiation is T dt dmr is -3 over these factors here. Kappa opacity, this is the luminosity at radius R divided R4 to the T to the 4. And then you can write this as in terms of this radiation nabla radiation, which is given by kappa LR times B over T4, with these are here kind of constant. Okay, so this is the variable determining that nabla radiation. Okay, now let's apply the radiative transport. So when you receive the light from the sun, it comes in about 8 minutes, traveling a distance of 150 million kilometers. However, this light needs maybe 50,000 years roughly to reach the surface of the sun. because it has to diffuse out by random walk. And now if the photon leaving the photosphere of the sun, yellow, okay, at the center of the sun, the temperature is 15 million. What is the color of the photon created there? What is the wavelength? So I give you this a homework. Think about the Wien's law, okay? So it's known that the star of mass between 0.25, 1.5 roughly, develop radiative core on the main sequence, while the star above 1.5, they are convective in the central core. Because actually, the reason is if we write the radiative gradient and we have this combination here, then it says that for the more massive star, the B over T to the 4 is roughly slowly varying, okay? Because they are radiation dominated, because the B is really B over T for almost not constant, but slowly varying. So then the radiative gradient is mainly determined by LR over MR. Okay, here is an example. You see this is stars with masses above 1.5. They have a convective core because they are not able to fuse the hydrogen to helium by the so-called proton-proton chain, but they have to use the CNO cycle. The CNO cycle is very sensitive to temperature, which is 10 to the 17 at 25 million, and therefore they cannot make the they cannot accomplish the radiation transport, the energy transport by radiation. So they have to do by convection, and this is because the opacity decreases toward the inner layer, and this is mainly Thomson scattering. Okay, and this becomes almost constant. But massive stars develop convective core on the main sequence, while if you talk about the sun has the radiative core, and you have it has the convective envelope, because the energy production in the sun is actually weakly dependent, relatively weakly dependent on the temperature, T to the 5 at 15 million. Okay. So actually the nebula radiative is the larger nebula adiabatic in this case here, which is called the Schwarzschild criterion, which I will show. Actually, let's go about the properties of the main sequence. So the star evolves usually with the time scale, the nuclear time scale is much larger than the Kelvin Helmholtz. So the energy equation, because of this long time scale, nuclear time scale, these terms with the time, they are actually, they compensate each other, so that you have DLR, DMR is just the difference between nuclear energy and neutrino, if neutrino are efficient, if they are acting at later stages. But you can collect these terms here. So the star will be then in mechanical and thermal equilibrium, or in hydrostatic and thermal equilibrium. So the nuclear luminosity appears at the surface. So these conditions are fulfilled during the main sequence. So now the physical meaning of the thermal equilibrium is that let's give you the temperature, the luminosity, and this is namely determined by the opacity. So if you see the lower the opacity, the brighter is the star. Okay, it's let's say at the end the star at the outer layer becomes optically thin. So then using this derivative of 8 T to the 4 over 3 and the equation I introduced before, then you see that the luminosity due to radiation is this expression here, and now the hydrostatic equilibrium means that we replace if we replace this derivative by B over R, and we go to this approximation. B is equal G M R squared over R to the 4, and then you see with the equation of state, let's say the gas constant over the molecular weight times rho of T, then you end up with this radiative luminosity is proportional to U to the power 4 times m to the power 3 over kappa, and so this is actually if you this is that depends of course on the mass distribution, but still it's an interesting relation, as we will see. If you use the so-called Kramer opacity, which is function of temperature and density, then you end up with the weak dependence of R, which is R to the square root of R. So the opacity, if the opacity is just as in massive stars is Thomson scattering opacity, then you have actually no dependence on R. Okay, because kappa is constant. So now the point is that what's really influenced the radius of the star? Okay, the answer is the thermonuclear energy source of the star, which is actually L nuclear is the nuclear energy generation times the energy density times the m, and so you see that if you take the CNO cycle with T to the 17, then you have 1 over R to the power 20, and this is clear dependence on the radius. So the nuclear energy production determines the radius of the star. So in thermal equilibrium, the L0 is L rod, which determine R uniquely, giving the mass and the initial composition of the star. Now I show you here, you see that that's actually the situation. You see here many stars evolving from the main sequence. This is the main sequence band, and you see the star here, the low mass star. This is 3, 2, 5, 9, and so on. And then you see actually this evolution from main sequence is proportional to the mean molecular weight. As you see here, 7.5, and here is 10 to the 4 due to the 4 when you go to mass. So these are actually the point of the main properties of the main sequence. Okay, now I still have how many minutes? How many?
10 more.
Yeah, okay, fine. Now, let's go to the convective energy transfer. I'm not going to go into the details again, but I have this. I've done this in the appendix 4. Okay, so let's give you an idea about convective energy transfer. I mean, you know, I'm not talking to the experts in the stellar evolution. I'm talking to eventually students who never heard about this or so, or they have a little idea about this. So therefore, I'm not talking to Oscar, for example, or to Ilma. So I just, this is cool, you know, and therefore I'm not so let's say demanding. So what is the basic picture actually? Convection is a dynamical instability. So okay, let me illustrate this. So this is now here you have a mass element. It's called bubble, for example, at radius r with temperature B, T, B, and density. So if you consider motion of this element to the r plus delta r, and will expand, right? And therefore it's illustrated. So this is the surrounding, and this is the element, right? Okay, so okay, now let's describe this by adiabatic motion. What is that? Actually, you assume, for simplicity, that the motion is adiabatic, means essentially no energy transport during the motion to the surrounding. But this is not right. So it will be corrected. And that can be done. But let's take it at adiabatic motion. So now the adiabatic mode, which means that the convection mass element has not enough time during the motion to exchange a appreciate amount of heat with the surrounding. Okay, so if you consider the density contrast, because the density in the element is smaller than the surrounding, so you see that the difference, the d rho dr of element minus d rho dr of the surrounding times delta r, because this is the distance of motion. So why the motion? Because of buoyancy force. Okay, so this is the buoyancy force is rho s of the surrounding times the gravitational acceleration. And now we have the downward gravitational force per unit volume is rho g a times c. Okay, so and now if we take the net force is the difference between the two, and we end up with g times delta rho. If the the d rho is negative, the element is lighter and goes upward, so unstable. If delta b is greater 0, element heavier and go down, stable situation. So therefore, you end up with demanding the condition for stability is this derivative c of the element minus that of surrounding greater than 0. But however, unfortunately, this is not a practical relation, because the density gradient do not appear in the basic equation of stellar evolution. And therefore, in principle, dPdr of the element requires, let's say, inclusion of heat exchange of the element with the surrounding. But if we just continue with the adiabatic motion and using some dynamics, including equation of state, and this derived again in the appendix, then you end up with this relation, which is the nabla is nabla element plus phi over delta times nabla mu, and this is the definition of this nablas here. This is the criterion for stability against convection, including the molecular mean molecular gradient, chemical gradient. And then you see that if you nabla describe the temperature variation in radiative layers, then you have nabla is equal nabla rad. And the question, when are the radiative layers unstable against convection? So if you go back to the adiabatic motion and we equate nabla to nabla adiabatic, then you have the so-called, actually, this is the Ledoux criterion in stellar physics. And this is the nabla rad is less than adiabatic plus this term, which takes into account the mean molecular weight. So if the layer is homogeneous, then this delta mu is 0, and then you end up with the Schwarzschild criterion for stability. What is the conclusion? The conclusion is delta mu has a stabilizing effect because the element of heavier material is pulled back by gravity, which I have shown up by equation 7. The term with nabla mu is positive, and therefore that's really harder to make convection by the Ledoux criterion. Usually the calculation is more related to the Schwarzschild criterion with some correction. Okay, here is an example. 25 solar mass. Well, again, I appreciate also all other calculation, but just I quoted this paper from my colleague in Clemson University. So this is a 25 solar mass star, and you see actually the main sequence, the hydrogen burning core decreases. You have a shell, hydrogen shell created, and you see here the helium phase, the helium burning phase, the helium core increasing in mass disappears, and this is with mass loss here. The envelope convective, You have a helium shell, C shell, C in the core, and C. We have calculated this beyond up to oxygen shell burning. So with all this using the Schwarzschild criterion and so on. So here you see that you can look at this detailed calculation in Space Science Review 2009. Okay, so far the first part, right? I just maybe 5 minutes for questions or so. I'm too fast, actually.
I think you're on time. You will have some time for questions as well, and for a maybe short coffee break. You can just grab your coffee and come back. Not that much. Okay.
We make
Thank you,
we make
Munir.
5 minutes break or what?
May I make a comment? Can you hear me now?
Oh,
yeah, Mauricio
Maurizio.
is here.
Maurizio.
Ciao Maurizio, buongiorno.
Ciao, I apologize. I had a lot of troubles with my audio systems. But if you now can hear me, I just want to suggest the students to memorize what Professor Elaide said just in the last comments, especially how he defined convection as an instability. That is something that they have to remind, and we'll come back tomorrow morning on that, on the issue of mixing. That's all.
Wonderful, wonderful. So I gave you the, let's say the.
In several points as usual, but we know each other very well.
Yeah, I know. I just the details are in the appendix actually, but I wanted to say, but then you are welcome to elaborate on this.
No, it's perfect. Thank you.
Okay, fine, that's fine. So what do we do now? We go 5 minutes break and come back.
Yes, good.
Yeah, I think that's a good idea. Yes, you're right. We're gonna pause the recording for a 5 minutes break and come back here on 25, maybe. 16.
Come back at 25.
Yeah.
Or what?
Time for coffee or tea. Thanks.
What do you want to?
20?
10:25.
Yeah, for you. Yes. Is that okay?
For me. For you, 11.
Yeah.
Okay,
Yeah.
fine. I wait a little bit and drink coffee or something and come back.
Okay.
And talk about
I'll be
nuclear
here
synthesis.
anyway.
And talk about nuclear synthesis.
Okay.
Okay.
So our attendees, if you can hear us, you can ask for questions if you like, or just grab your coffee and come back in 5 minutes.
You can. They can ask questions, please.
You can use the question and answers tab. You can raise your hand. We will allow you to talk. We had 40 attendees. Some of them just dropped. So we have 32 attendees right now and 14 panelists.
And this is also not to, I don't know if this is really well known also. In any case, I am assuming that is not well known. So I'm going to talk about how do we define nuclear reaction rates. Okay. I think I'm going to go to the cross section, the astrophysical S factor, the Kramov peak, and I present the reaction rate for non-resonant reactions. I'm talking about making elements, heavy elements, and isotopes. Okay, so what is the cross section? Cross section is the number of reaction per nucleotide per second divided by the number of the incident particles per area and second. So if we define the nx, the number of the type X, and A is the number of type A, then we have the sigma, the cross section, is function of relative velocity because they have to meet. So then you have the reaction, for example, A, the particles could be a proton, for example. X could be a carbon, could be whatever. Okay. And then it goes to the residual nucleus, Y, plus the ejected particles, P. So the reaction rate is the effective area, sigma times nx. Nx is the number density of the incoming, of the target, okay? Times the particle flux is velocity, relative velocity times Na, the number density of type A. And this is given in the cubic centimeter and second. But the star, in the star, we deal with plasma, which is in which the particles have a spectrum of velocities and not only one single number. So we have phi of b, so that we normalize from 0 to infinity, phi of d dv equal to 1. So we need to calculate the average of, now in the bracket here, sigma v equal to 0 to infinity, phi of v sigma v dv. This is folding of the phi of v. Okay. And so the reaction rate is now the product of nx and A times the average of sigma v. This is if A is not x. For example, you may have two protons reacting, therefore they are identical. If you are identical, the A identical x, then you have to avoid double counting. So therefore you write a factor with the chronicle delta function, and it's essentially divided by 2. Okay, and then you multiply by an x. So this is now delta is 1 for A equal x and 0 for A not x. Okay, so this will avoid double counting. So what is the lifetime? The lifetime is, of course, the nx is decreasing, and therefore you have nx over tau, because decreasing in the lifetime. Okay, and therefore you have nx dnx dta is minus sigma ax and x, and you write this as nx over tau, and then you have actually, this is you take into account the two particles are interacting identical, you have to multiply by 2. So equating both expressions, you end up with the tau. If A react with x, then you have 1 over Na times the average of sigma v between the two particles. So if you have, if a nucleus X is destroyed by 7 reactions, then you have to sum up. Okay. Now, what is then now the form of the velocity phi of v? Because we have introduced this phi of v without saying anything about it. So the nuclei in stars, plasma, are certainly non-degenerate owing to their high masses. And this is the normal stellar evolution. Okay. So in thermodynamic equilibrium, the velocity distribution is described by the Maxwell-Bosman distribution. Okay, and here is it. Phi of v is 4 that goes up like d squared and decrease like exponential minus, this is the kinetic energy compared to the k times t. So you see here, average value, RMS value, maximum, and so on. You see also the Maxwell distribution function of velocity, of temperature. And then you see that, of course, this is well-known behavior. Okay, now our concern is to find the correct average of sigma VAX. Now, since the cross-section depends on the relative velocity, and the nuclei in the stellar interior have Maxwell-Bosman distribution, we can express the average above in terms of the reduced mass and kinetic energy. And this leads to sigma V, this KT to the power minus 3/2, 0 to infinity, dE sigma of E times the exponential minus E over KT. Okay, given sigma of E, we end up with a simple integration. Okay, and we define now the rate, the lambda is sigma. Let's write as sigma VAX. This is just lambda x for just make it short. So now we want to obtain a simple expression of sigma of E. Okay, first of all, sigma is proportional to lambda squared dB. dB is the de Broglie wavelength. And also we can write it as proportional 1 over E. Okay. And also we have a tunnel effect because there's a penetration, there's a Coulomb barrier. And therefore the sigma is proportional to exponential, this is a constant for, I have it later, divided by the square root of E. This is the tunnel effect, okay? Clear. So sigma E is now 1 over E, geometrical factor, times the tunneling factor, which is exponential minus B over square root of E. And now we have a nuclear factor, which they have to be either determined by experiment or also by a theoretical approach. But this is really the relation of sigma of E. Okay, now finally, we introduce this SE exponential minus E over KT exponential minus B over square root of E. And now you see the B is the function of the charges of the reacting species. And this is a mean molecular mean mass. It's AX over, there must be a plus here. This is the mean mass number. So if S of E is slowly varying function, then we are talking about non-resonant reaction. We can take it outside the integral. And then we end up saying this reaction rate, this lambda, is going to be determined by the combination of two exponentials. And this is what I show you in the next, this is here, sorry, this is, must be blurred. One of them, okay, I can correct this, okay. So, okay, so now let's consider the Maxwell-Bosman distribution. This is proportional exponential minus E over KT. It has this shape. And then you have the tunnel effect, the Coulomb barrier, which is this square root of 1 over square root of E. So if you combine them, then you have, this is exaggerated actually. You have the so-called Karamov peak, which is magnified to show it better. So you see the maximum here is something between 15 and 30 kb. And here is the K between 1 to 3 of kilo electron volt. And this is the secret of thermonuclear reaction in stars. Without this, we cannot exist, actually. Most of the reaction will occur in the high energy tail of the Maxwell-Bosman distribution, as you see indicated here. So the fact that E0 is much larger than K times T is due to the penetration factor pushing it to higher energy. Okay, but actually the calm of peak is asymmetrical distribution. And it has to be done in kind of symmetrical way. I will come back to this. But let's determine E0. Okay, you take the function g of E times the multiplication of the two exponentials, and you make the derivative, put a 0 to get the maximum, and you end up with the B times K times T over 2 to the power 2/3, which you can be written as in this way, when mu is related to the atomic mass units, and T6 is T over 1 million degrees. Okay, so when you see here, let's take the so-called proton-proton chain, which is happening in the sun, the fusion of hydrogen to helium in the sun. And if we take T6 equal 15, then we have E0 5.9 kilo electron volt. If we take helium-4 reacting with carbon-12 at 15 T6 equal 15, then you have factor 26.5. Now, if you consider oxygen fusion, oxygen plus oxygen, again at the same temperature, you have factor 237. So what is the meaning of this? The meaning of this is that the calm of peak is shifted to higher energy as the nuclear charge is increasing. And this is the net effect of the Coulomb barrier. So you have to penetrate in order to the region of the nucleus in order to make the reaction. Okay, now the reaction rate for non-resonant reaction, the asymmetric calm of peak can be transformed into symmetric Gaussian distribution. And we obtain, after a little bit of a bit of detailed calculation, if someone interested, I can supply this. We obtain the reaction rate, and you see here, in terms of the mass fraction, mass number times the abundance divided by the density times the Avogadro number. Tau is defined by this combination of charges and mu, which I have introduced. But then you see here the point. The point is that you have rho squared, which defines the reaction of two partners. And then you have the astrophysical factor 0 as 0. And then you have tau squared, and this is exponential minus tau. And this is in centimeter cube of a second. And this exponential dependence here is reflecting the tunnel effect. Absolutely. So and now, okay, so far, in very short, and to actually pointing out the role of the common factor, which is an essential thing in thermonuclear reaction. Okay, whether theoretical or experimental, the calm of peak is an amazing discovery by Kant. Okay, let's stop, and before I proceed, just to have 1 minute to think, I quote Herman Weyl. He said, "My work always tried to unite the true with the beautiful, but when I had to choose between one or the other, I usually choose the beautiful." This is amazing. I like this sentence. Okay, now let me show you the helium fusion. And this is actually a resonant reaction. And it consists of two then this is the way to red giant, right? This is the two-step process. The helium-4 plus helium-4 goes to beryllium-8, but beryllium-8 is unstable. So in the lab, it goes back. But the red giant, owing to the high density, succeeds to capture another helium to go into carbon-12. Why is that so? Because actually there is a state, a quantum state in the carbon-12, which is 7.654 mega electron volt. This state enables the fusion of the two processes, enable the creation of the carbon in the universe. And now you see that the exponential dependence of the reaction rate can be written in a power law. And that turns out to be the triple alpha, because you see 1, 2, 3 particle, alpha particles, or helium-4, and making one carbon plus radiation. So you see that actually this is T to the power 41. It's very sensitive. And that makes helium flash in core helium flash and thermal position AGB stars. Somebody is going to talk about AGB stars. And this is because the helium is so sensitive to temperature. And now the other point is that you make a carbon-12, but then carbon-12 will react with helium to make the oxygen-16, but the oxygen-16 survives because of the no resonance involved. So this is one essential fusion process in the theory of stellar evolution. This is the way to red giant and the creation of the carbon. Okay, now here is the 20 solar mass star. I have shown this with mass loss, and this is what's happening here in the helium core when the star evolves to the red giant. Okay, and then you have helium shell and C shell, and you have carbon convective core, shell convection, oxygen core, oxygen shell. It's complicated. Details here in this paper, if you want. Of course, there are other calculations. So just I mentioned this one. Okay, now let's go to the path of the heavy elements. Okay, here you see the let's say Z, the number of protons, and this is the number of neutrons. And now you see actually this is the beta value of stability, and you see the S process is just this black zigzag line, and you see the R process is going to the neutron-rich side and stocks at the magic numbers 50, 82, and 126. So if then here is the S process path, and then you cannot go to the super heavy because they decay back. So you cannot make super heavy like uranium and thorium and so on because of alpha decay. So how do you make them? By the R process, because it goes back and by beta decay, which is the here is this raining to the stability valley, and otherwise you have N gamma reaction. This is neutron capture, because you cannot make heavy element without neutron. Okay, so let's go about talk about a little bit of details of the S process. So I have selected the S process because I have more information about this than I'm more informed about the S process than the R process. So therefore, actually the S process starts with iron 56. The neutron source are carbon 12 P gamma N13, C13 alpha N, or you also have, this is AGB stars, and the massive stars, they go to neon 22 alpha N to magnesium 25 to produce the neutron. So the neutron spectrum has Maxwell Bosman distribution. The temperature is between 25 and 30 kilo electron volt, which is something like 1.5 to 3.5 10 to the 8 Kelvin. The time scale is that the neutron capture is much less than the beta decay, which is a range of 10 to the 100 years. And we have the S process going on in massive stars, part of it, but most of it internally pulsating AGB stars, which is the playground of Maurizio and Oscar. I think they are going to talk about it somehow. Okay, so let me give you a little bit of insight. I have actually, how much time I have then, because I have just not much. We still have time. What time I still have?
Well, you still have 15 minutes or so, even more than that.
Yeah, okay.
Oh.
So let me introduce the sigma NS curve. So actually, the neutron capture will proceed by thermalized neutrons. Yeah, and this is elastic scattering in the stellar plasma. So the neutrons obey the Maxwell-Bosman distribution, which I have introduced. From the lab experiment, you know that cross-section for neutron capture is 1 over velocity, or 1 over square root of E, and this is L0 S-wave scattering. So if you then compare the Maxwell-Bosman distribution with this red curve, which is proportional to 1 over the energy, and then you have maximum A0 at equal KT. So this is A0 is the most probable energy. So the time of velocity of neutrons is 2k times T over M to the power 1/2. And therefore, the above energy dependence is actually, if you take sigma V, is constant. And this you can write as sigma thermal times V thermal. So, and therefore you have an average cross section, which is sigma average of sigma V over VT, where this sigma V is the integral of sigma V phi of V Maxwell folded again. Okay, and that okay, so and we end up sigma equals sigma T for sigma proportional 1 over V. There is also a situation with higher energy actually, which is sigma T times 2 over pi if the sigma behaves like 1 over V squared. Then let me show you actually what happened really in the S process. So this is the neutron number, and this is the proton number. So if you have a nucleus, oh, this is a little bit hidden. Okay, so this is Z A minus 1, and this is ZA here. And that's actually neutron. If you capture a neutron by ZA minus 1, you go to this red nucleus here. So this is the ZA plus gamma. And now ZA goes to make better because radioactive, it goes to ZA nucleus and emitting electron and neutrino. Actually, anti-neutrino. So this is beta minus decay. So if you then take the derivative NS for the S element, abundance, AT, then you have a creation this way, and you have a destruction by lambda NA and by beta decay. So, and this is the coupled system of differential equation. So if we take the lambda n times sigma n gamma, then we can write this for, as I told you, by the thermal velocity, and then we have dn times sigma. And now lambda n is now the number density of neutron written in terms of Vt is actually this is, I repeated this or so. Yeah, oh sorry. And lambda beta is ln over 2 divided by the lifetime, but the lifetime is affected by the condition in the stellar plasma. So you have to modify the beta minus decay. Okay, and now we arrived at the sigma and s shortly. So let's define the neutron exposure, which is phi n dt. And using this relation here, we get actually we transform this to the tau, and then we have the product sigma a minus 1 ns a minus 1 minus sigma a ns a. So we will introduce again the n times vt, and we know that tau beta is much less than n. So then we end up let's say the above equation, this self-regulated here. So NA decreases if greater than n minus a and vice versa. And therefore you end up with sigma a NA is sigma a minus 1 NA minus 1. So therefore this says that nucleons with smaller sigma would have higher dependence, but the nucleons with large sigma, the small dependence. And this is verified here in this number. You see here actually the sigma ns curve. This is the AGB contribution, and this is the weak component in mass of stars. So they go up, and not the this is the division is at A equal 90. Okay, so this is the proof of the S process happening in AGB star and massive stars. Okay, here is the summary of the abundance curve of elements, and you see actually the light elements. You see the iron here, big, and you see the R, S, and also P process, and you see that the binding energy per nucleon is has a maximum at the iron region, and therefore this explains why the iron is so abundant. While these heavy elements are actually declined, they are very small, cannot be produced so heavily like the less heavy elements. So a lot of process here involved in carbon burning, helium burning, cosmological, cosmic ray, hydrogen burning, oxygen burning, and so on. Okay, so far I gave you a little bit of insight about nucleosynthesis, and well, this is what I have collected. And so we have some time for question if you want.
Thanks, Munib. It was great effort to collect them all and give in such short amount of time. And we have 39 attendees now. If you have any questions, please raise your hand so that we can start talking. Or if you like, you can write down in the chat or question and answers. Inma answered this, but we have one question. What is the Coulomb barrier?
The Coulomb barrier?
Mm-hmm.
Well, this is because the nuclei have have charge. So and then if you this is the Coulomb law, which is similar to the gravity, to the gravitational equation. This is the product of charges divided by R squared times the Coulomb constant. So
Yes,
that
okay.
actually, because if you want to have, let's say, take a proton, react with carbon 12, or proton react with the other proton. So then you see that if you have two protons, then the Coulomb barrier is much less than when you have proton reacting with carbon 12, because you have six protons reacting with one instead of 1 to 1. And therefore, this is expressed by the penetration factor, which is the tunnel effect in quantum mechanics. So you cannot understand star without quantum mechanics.
For sure.
Okay. So this is
Yes, I guess
actually
it is answered.
statistical mechanics and quantum mechanics combined together to give you the Karamov peak.
Yeah, if I can add something, we do not know exactly what is the background of the students. There will be an average, but there will be also differences. Maybe I invite the students to tell us, for example, if they need some integrations on what Professor Reid said concerning modern physics, how quantum mechanics establishes the possibility to overcome the Coulomb barrier. If they need some integrations, any one of us, independent of the topic we were assigned, can do that. Munib himself, or I, or Oscar Samir, whoever.
Actually, I can, yes, if somebody is not familiar with this tunnel effect, I can very simple in 10 minutes explain to him what's going on.
Yeah.
Okay.
Okay. We'll make a poll about it. Maybe later on we can add some another 10 minutes.
See that,
right
that we can make a, for example, in the afternoon also. I can come back to describe actually what happens then in the case of the tunnel effect. Is not only reaction into the nucleus, also the alpha decay is also tunneling, because you have the alpha particle, the helium, the alpha particle has to go from uranium, for example, then it has to penetrate. Okay, so this is a basic issue in quantum mechanics, actually.
Right.
Well, we can explain this very easily. No problem. So you cannot react to particles without taking care about the Coulomb repulsion. Right? So, and because the two charges, let's say proton plus proton, had to have high energy, like in the sun. Why is the central temperature of the sun 15 million? Because they have to go close to each other to 10 to minus 15 meter in order to feel the strong force. To undergo fusion. Okay.
Yes, we have opened up the discussion on Slack right now. If Mauricio did that, actually.
Just to try.
It will be nice if anybody responds. We'll give another expansion for this lecture. Well, we started with the hard course, and then we are going to continue today in 1.5 hours. Now we have a lunch break. I don't see any questions right now on Zoom, but we will be collecting your questions also from Slack. And if you have, if you want an extra expansion for this lecture by Munib 8, we're going to do it in the afternoon. I will let you know.
Yes.
Okay. So
just to stop, sorry if I am speaking too much, but
No.
Munib made a very nice talk, and I say he mentioned the S process, and he mentioned the kind of reactions we need to drive neutron captures, okay? One of these reactions is the carbon-13 alpha N. It's very tricky because in helium burning regions, you don't expect to have much carbon-13. So this is another issue in which the physics and the nucleosynthesis in stars addressed by Professor Elaide has a crucial something to do with mixing. So we'll come back maybe in my second hour tomorrow morning on how to mix protons into the helium layers to produce carbon-13.
Yeah, maybe.
That's all.
That's very difficult. This is the AGB phase.
Yeah.
So it's a small region where you have the carbon-13 acting.
Yeah, we'll see something tomorrow.
Yeah. This can be, maybe you can make a little bit of explanation about how is this working in the AGB stars.
Oscar has something to say. Please, Oscar.
Yeah. Oh, yeah. Can you hear me?
Yep.
Okay. I would simply add that when you look to a cross section of a nuclear process, of a nuclear reactions like the ones you have explained, Munib, there are two parts. Two probability is the product of two probability. One is the part that concern the electric repulsion between the charged particles that are interacting. And the second part is the nuclear part, the potential inside the compound nucleus that forms after the fusions. While the electric part, the Coulomb part is quite well understood. What the part in which we have major ignorance is the nuclear part, and this is because the theory involved, that is the quantum chromodynamics, is something very complicated, especially when we have compound nuclei which are composed by many particles, many protons and neutrons. And this is very difficult to get solutions of the quantum chromodynamics equations starting exact solutions of these equations. So this is to say that in order to understand nuclear reaction at low energy in stars, it becomes very important to have precise experiment in laboratory that can provide us information about this nuclear part. Okay, so this is an important thing that we have to remember, that nuclear physics experiments in the low energy part of the energy spectrum is fundamental to understand stars.
Yeah, this is the astrophysical factor, right? This is the S factor.
Yes, exactly. Yes, when you
in the cross section, exactly.
Yeah.
So this is because it happens at low energy, and the experiments most of the time they are not going to so far to just to pick up the regular value. So you have to somehow make a theoretical or extrapolation or whatever. Right? So actually, I omitted a lot of details because I put S of E equal S0, so a lot of correction there and so on. The nuclear factor, Oscar, this is really, the nuclear factor is the most important and also unsecure case in the nuclear reactions.
Yes, I agree. Yes, and just to complete the concept, probably the only reaction for which we have theoretical informations, because it's an easier problem, is the PP reaction, P plus P reaction, that is very important in the sun. And now there are some calculations for the D plus P reactions. But when you consider more reactions in which more nucleons participate in forming the compound nucleus, the calculation become impossible. So experiments, we have to rely on experiments.
Yeah.
For example, you have mentioned that the famous problem of the status in the carbon 12 nucleus, firstly proposed by Fred Hoyle in order to allow stars to produce carbon. And, and then this was a very incredible intuition by Fred Hoyle. And the Pasadena group of Willie Fowler later on made the experiment and found the state exactly where Fred Hoyle predicted it. This was very famous case in which an intuition of a theoreticians guided the experiments, but the experiments, but the final word was from the experiment.
That is connected to many things in science history that maybe in some pause, in some relaxing moment, it might be nice to tell the students, for example, from the adventure that Oscar was mentioning, William Fowler got the Nobel Prize and Fred Hoyle didn't. So this is one of the many quarrels developed in our field.
Actually, that was for me was fascinating that the carbon production is depending on one single resonance state in the carbon core. This is actually amazing.
Not only the carbon production, whatever is heavier than helium.
Yeah, but this.
Without it, we were not here to speak about that.
But I'm actually, that's one I want to tell the students, so that listen, that actually the quantum mechanics is you cannot understand the universe and the stars without quantum mechanics. You cannot understand stars without quantum mechanics. This is my point.
Absolutely.
So, okay. So when do we meet? When will you meet again?
We are going to meet in 1.5 hours.
This is your time. What is your time is what?
Sorry, not 1.5 hours. Now that it is 12 in my hour. We have a 20-minute break. It's not the lunch break. Sorry. We're gonna meet in 20 minutes in 1:30, whatever your time right now is.
Wait a minute. This is now lunch break till.
No, yeah, for some people it will be lunch break. For others, it's coffee break. I don't know what you call it. It's
Munich 10:30 for us. 10:30.
Yeah.
In Central Europe, it is say brunch break.
Well, my time.
Some people have brunch break now.
My time is 11 here in Beirut.
Okay, so 11:30 for you. Yes.
So for you, it's brunch time, even more than for us, which is for us it's 10 o'clock.
We have.
See you, everyone.
Actually, the next lecture is at 2 or something in your time.
No.
We have just a 20-minute break right now, and then we will have a bigger break later on.
Okay.
Before your student starts to talk.
Fine.
Okay.
Thank you.
Okay then. See you in 20 minutes. And you can use the same link.
See you. Bye.
For today. See you. Take care.
See you. Bye.
Okay, recording started. Our second session on Monday is going to start with observational astronomy. Dr. Sinan Alish, a colleague of mine from Istanbul University, is going to start with observation of astronomy topics. He's going to cover 2 lectures, starting with surveys in astronomy, as I see.
Yeah, the problem is that it doesn't see, Zoom doesn't see my second screen. So I don't know why it's happening. First time I see this, it's very strange. Okay, I don't want to spend so much time. The bad thing is that you may see the presentation. I mean, let me see. Yeah, whatever I do, you will see the presentation note.
We see it well.
Yeah, that's okay, but you can actually switch it to the right maybe a little bit, or close the tabs, sidebars. That would be enough.
If I do like this, like that. Okay, I switch this to here. No. I don't understand why the computer doesn't see my second screen, but okay, doesn't matter. Or yeah, okay, just a
Can you
moment.
change the side of the current slide view?
Okay, now it's fine.
Okay.
I disabled the screen. Okay, hello everybody. I will talk about surveys in astronomy in general. I will make a quick overview of imaging and spectroscopic survey, and then we'll talk about some instrumentation related to those surveys. But to be honest, I will mostly emphasize on the spectroscopic side, because I think we are now in the era of the spectroscopic surveys rather than imaging ones. Imaging surveys have almost completed their mission. Of course, they are still valuable and continue, but nowadays we are in a period changing from imaging survey to the spectroscopic survey. So I want to spend more time on the spectroscopic side. So let's start. So of course, in this talk, even it can be seen as quite long in time, but it's not enough to cover all the historical perspective. So I cannot go back to all the history, but one particular case is very important, which is the Pos Survey. It is done in 1950s in the Palomar Observatory in California. And nowadays we are using this data as for observation planning, or some checking for some transient sources, especially because we have a record from the 1950s, and so we can compare the recent surveys, recent images of the same sky with the 1950s. So it is done in the north and south from the US national observatories, both skies. So that we have whole sky survey. This is one of the first completed whole sky survey of the night sky. And of course, at that time we didn't have CCD technology, so all this survey was completed using glass plates, and then they were digitized. And nowadays we can access to those digitized data through several mirrors, several sites. And one of the other important thing is that is the infrared astronomy, because we are now also in another period. It's not recently starting, but already started some time ago. Optical astronomy is not enough itself for covering many topics. So optical plus near infrared is very important. And a similar attempt for covering all sky is done by 2MASS survey. It's 2 micron all sky survey. Actually, it started with only one single band, but then it's enlarged to the three bands. So nowadays we have J, H, and KS bands, sky photometric data, imaging data of the whole sky from north and south again. It was completed around at the beginning of the 21st century. And the only thing is that the 2MASS survey is not too deep. It's compared to many imaging surveys nowadays, it can be considered as shallow. So we don't have so much galaxies compared to stars. So 2MASS is mostly applicable or useful for galactic studies rather than extragalactic ones. But still there are some, of course, nearby galaxies included in the 2MASS survey, but not so distant galaxies, distant sources. So the important point about 2MASS survey is that they set the standard of the near infrared passband. So we are now using this near infrared passbands because of the TUMAS, because since we have all sky survey based on this based on these bands, and following surveys or instrumentation, they also follow the same standards about the filter band passes. So today, JHK and K short, KS is the general standard for the near infrared imaging. We have some extended object catalogs as well, like galaxy clusters or nearby galaxies and large extended objects, also recorded and also detected by the TUMAS sources. But of course, the most important imaging surveys in the 21st century, the last 20 years, is the STSS, because it started with 2000 and it was maybe not expected that much, but it affects and impact on astronomy is really huge. And nowadays, still we are continuing to develop and use the STSS. So now one of the most recent data releases is 16, starting from 2000. 2001, we have 16 data releases, and actually, okay, there are some Turkish words, but actually we have more than 1 trillion objects and photometric data of 1 trillion objects in the STSS database. STSS is performed from the New Mexico in the United States, so it's a northern sky survey, so it doesn't go so much below the equator, and even so, actually, it is not completed in the northern sky, on the whole northern sky, but it's big portion of the northern sky was covered by STSS. The other important thing is that later on, during the survey, they started with the spectroscopic follow-up of the STSS sources, but of course, it is not enough to go deeper and having large number of objects, because STSS survey was performed and is being performed by a 2.5 meter telescope. It's not a huge telescope, so it requires more and more exposure time to go deeper and to observe galaxies. So as a result, we don't have so many galaxy spectra or quasar spectra when compared with the photometric objects detected by STSS. Number of photometric objects is huge, but they don't have spectra for all of those things. In the meantime, they developed some special surveys within the STSS. They called like BOS, eBOS, or Apogee, different spectroscopic surveys performed, and most of them targeted to the galaxies and the extragalactic astronomy. Some of them targeted to the galactic studies like Apogee and Marvel. Here you can see some example spectra from the STSS. And one of the other imaging surveys, CFHTLS, is not a huge survey, I mean, in terms of the sky coverage, but one of the deepest surveys so far. And in the meantime, in these days, actually, Subaru Hyper Supreme Camp survey now is going deeper than the CFHTLS, but up to the Subaru, actually CFHTLS was one of the deepest imaging survey in the astronomy, but it's only 170 square degree, not so large. When you compare the STSS 10,000 square degrees, it's not a huge survey, but it's one of the deepest survey. At this point, I want to emphasize one important discrimination in surveys, especially imaging surveys or even spectroscopic surveys. We have two kind of strategies. The first strategy is the whole sky survey or the large sky surveys. If it is possible, the whole sky is preferable, but if it is not possible, of course, we would like to have as much as possible of the sky. But then there's a second approach, is that we observe a deeper, very smaller area, but deeper area. In that latter case, we call these surveys pencil beam surveys because of the geometrical structure. It looks like a pencil beam, the extreme part of the pencils, the shape. So we started from a very small angle, but we go deeper And as a result, our solid angle extended as we go deep and deep. And those kind of surveys mostly used for evolution or the cosmic evolution of the cosmic structures, in very generally, I can say that. But so far, I'm talking about large sky surveys or whole sky survey. Okay. So I will be a little bit fast, so maybe we can discuss and you can ask questions afterwards if you want. And details are here, so I can share the slides for you. One of the other important surveys is the DES. DES is performed from the southern sky using the 4-meter Blanco telescope. So it's called the Dark Energy Survey. The initial aim was the 5,000 square degrees, and it was completed recently. And now they are extending the survey for larger area. One of the main target of the DES survey actually to pinpoint the type 1a supernovae, to use them for the expansion, to use them to extract the expansion history of the universe. But in the meantime, of course, the survey can be used for many purposes like galaxy studies or transient objects and many purposes. Here are the numbers, so I don't repeat them. I don't read them, so you can go through. This is some snapshots from the DES survey. So this is the Decamp Camera, one of the most advanced and camera in the astronomy. It's very large, and this camera is installed at the prime focus of the Blanco telescope. As you can see, this is a horseshoe design, very old telescope from the 1970s, but it is modernized by this camera, and they transformed the prime focus to a complete instrument like that. So they used for the survey. The advantage of having a large mosaic camera is to detect, or is to observe the sky larger area for each pointing, so you don't spend so much time to cover large areas. So for imaging surveys, actually a mosaic camera is a must. Otherwise, with a single and classical just one camera, you cannot conduct a large sky survey. This is again the view of the mosaic of the different CCDs and some astrometric and photometric accuracies and properties of the DES sky survey. This is the magnitude limit. For imaging surveys, or also for spectroscopic surveys in general, there is one very important parameter, is the completeness. So each survey has to define very well the completeness limits of their analysis, because otherwise you cannot use this data for with a homogeneous approach or with a homogeneous purposes. So here there are some limits. Generally, the different surveys on different studies, they give different levels, but sometimes they can give as 80% completeness, or sometimes, as you can see here, almost 100% completeness levels. So it means that at this magnitude levels for these bands, the survey detects all the objects in that sky area. Okay, so they are complete. This is the completeness curves, how they behave. Another important survey is the VISTA. It is for infrared astronomy, actually, visible and infrared survey telescope, but VISTA survey is mostly conducted in the infrared bands. As you can see here, the bands. It starts with the Y band, but mostly it goes Z and Y, but mostly it's in the infrared bands. So there are several surveys done in the VISTA, and still it's continuing. And soon it will be stopped for another purpose. I will tell you about that. I'm so sorry, just a minute. Bitti mi? Oldu mu? Tamam. Tamam. Çok about that because I'm alone and having to take care of something. So VISTA is done in many different strategies in the sky, mostly galactic and extragalactic purposes. And you can read details, so I need to spend my time economically. And this is the VISTA telescope. This telescope is soon to be transformed for a spectroscopic facility. I will talk about that later, but I can just mention that its name going to be foremost afterwards, after this transition. So the imaging survey is, the infrared imaging survey is conducted with this mosaic camera here, as you can see, the 16 CCD, again in these bands, but mostly J, H, and KS, of course. But in some cases, they extended the strategy for other bands as well. Okay. There is one smaller telescope, is 2.5 meter telescope, VLT survey telescope. They both VISTA and VST. They are located in the parallel and next to the VLT telescopes. So VST actually a smaller telescope, but it has a powerful camera, which is called Omega Cam. And with this powerful camera, actually, it's possible to study the weak lensing studies. So the sharpness of the images is quite impressive. Even the telescope is smaller. And so it is used for many weak lensing studies and mass estimates of massive structures like galaxy clusters and some other objects. Okay, of course, the most famous nowadays is the Rubin Observatory. Previously it's known as LSST, you know, Large Synoptic Survey Telescope. And after the Vera Rubin, it's now renamed as the Rubin Observatory. So this is an 8.4 meter gigantic telescope for imaging survey. And actually this will really encompass the Sloan capabilities, but of course they are not targeting at the same sky. So Rubin Observatory will be in the southern, it's located in the Chile, again, in the Atacama desert. So Rubin Observatory, the Rubin telescope is a huge telescope, so it will go deeper, much deeper than any existing imaging survey, and in a very short period of time. But the main target, aim of the purpose of the Rubin Observatory is to detect transient objects. So it has a huge camera and a very interesting design. I am not going into details now, but we can discuss. It has a very different design than classical telescopes like VISTA, and they have, as a result of the design or more optical design, they have a quite large field of view, because for a typical telescope like that, 8 meter telescope, you cannot reach that kind of field of views, which is 3.5 degrees, square degrees. Is huge for this kind of telescope. It means that Rubin Observatory, or LSST, whichever you call, LSST will cover whole sky, I mean whole southern sky, every 3 days, because it is a huge telescope. It is very speed, so it doesn't need to expose too long. So in a short exposure, it will go deeper, like 25, 26, 27 magnitudes in different passbands. So it will cover whole sky in 3 days, and every 3 nights, it will repeat the whole sky. So as a result of that, we can detect any transient objects in every 3 days. We will have a reference frame, so we can compare the previous 3 days, previous observation of three nights ago, and then we can detect any transient objects in terms of, you know, positioning and in terms of brightness. So here are some, again, the details of the strategy. So as you can see, LSST will go to completeness level of LSST is going to almost 27 magnitude, which is really huge because we don't have such a deep data now. So when LSST starts its operations, we will have enormous data, and this data will be immediately public, because it will be huge data every night in the order of terabytes of data. 20, 30 terabytes of data will be produced for every night, and so it's a very huge data storage in the end. So this is the survey footprint or survey strategy of the LSST. As it is in the south, of course, it will cover the southern sky, but some equatorial regions also can be covered and can be commonly observed in the northern telescopes as well. So it can be used as a reference and comparison with the existing surveys like STSS. So here there are the huge numbers of LSST. This is one of the gigantic projects in the astronomy, and it will be operational very soon, very soon. In 1 or 2 years, I think we can see that LSST will started. Another important project, it is not gigantic, but it is a very important, deep, is the Hyper Supreme Cam. So the Japanese observatory, they transformed the Subaru telescope to a survey telescope by replacing its prime focus again. So first of all, they installed a very sharp camera and new optics and sharp camera. So they started an imaging survey, which is called Hyper Supreme Cam Subaru Strategic Program, which is a very long name, or HSC shortly. The HSC surveys, they have 3 different fields and strategy: wide, deep, and ultra deep fields. The widest field is 1400 square degree, which is not so huge when you compare the STSS, of course, but the magnitude limit is comparable like the LSST, which is not started yet, but on more or less the same order, 26 magnitude. So at the moment, this is the deepest imaging survey existing. But again, this is mostly in the equatorial plane, because Subaru telescope is also located in the Hawaii. It is Northern Observatory, but as a strategy, they don't go so much higher in terms of altitude, in terms of declination. So they observe the equatorial part mostly for scientific reasons. So here are some observing strategy and how much time needed to complete the survey. It is given here. For any kind of survey, actually, you need to allocate lots of time. For instance, for HSC surveys, 300, actually in the end it's more than 300, but more than 300 nights were allocated from the Subaru telescope. This is a huge telescope time, and this is always a big tension between the community who is using the telescope and the big projects, because they need the telescope, but then you decide to allocate the telescope for another purpose. So it's always a big tension. It's not easy. For instance, from CFHT, Subaru, this kind of telescopes are normally used for other purposes or general usage from their communities. So it's hard to transform them to a survey telescope. But in the case of VISTA, STSS, LSST, they are designed from the beginning as a survey telescope, and there is no tension about that. And they are planned and they are continuing their observation. Okay, this is again the mosaic camera of the Subaru HSC survey. As I said, it's always needed a mosaic camera to have a larger field of view, because you need to use your time efficiently. This is one of the way to increase the efficiency in terms of time. Another, of course, I don't mention explicitly all the time, but in a classical telescope, if you want to observe a larger field of view, you have to go to the prime focus, because prime focus is the theoretical, or let's say the technical limit of the field of view of a telescope. So there is no larger field of view other than prime focus. So in many telescope projects, in many survey projects, they started to use prime focus. Normally, we don't use prime focus because our instruments are very heavy and we cannot put them to the prime focus. It's not so feasible. But for this specific purposes, telescopes are transformed, and so they are using their prime focus to have larger field of views. Okay. So there are some survey footprints in comparison, like STSS, different STSS survey like BOS, eBOS, and the DES surveys like DEC. It's called with DEC ALS because DEC is a dark energy camera, so they're using these initials. There's Vipers I will talk about in the second, soon. CFHTS Vipers, DES here, and also HSC surveys are also located here. And this is the imaging survey so far. Now I want to talk about the last part, in this last part of the first half, about the spectroscopic surveys. So it started also with Sloan STSS survey to have spectra of many objects, but afterwards different projects conducted. Some of them are used VLT telescope, like in the case of VLT Vimus, or there is Deimos spectrograph installed at Keck telescopes, and different telescopes instruments were used for the spectroscopic survey for this purpose. But what was the purpose? Why we are having spectra of many objects? There are two main boulevard in this studies. One is cosmology, to have larger many galaxies, so to characterize the cosmic structures in many ways. But generally we call them, let's say, for the cosmological purposes. The other second purposes is for galactic studies, and to get the chemical abundances or chemical structure of our own galaxy, Milky Way. And so it is used for two different purposes, two main purposes, but there are lots of details, of course. Okay, this is also just to reminding you some footprints about major surveys. I will continue about that. So I will just mention now quickly about some surveys about cosmic structures. And in the case of cosmology, actually what we need at first hand is the redshifts. But I mean, I'm talking about spectroscopic redshifts. Of course, nowadays we are able to compute photometric redshifts as well. But they can be used with very high limitations or used with a caution. So in general, for the evolution of the cosmic structures, like the characterization of the large-scale structure, as you can see, or mass measurement of galaxy clusters, or for this kind of studies, you need spectroscopic redshifts. So many spectroscopic survey in the first place aimed to have redshifts of thousands of galaxies. Okay. In the beginning, there were 2DF GRS survey from Anglo-Australian telescope. Then STSS started, and even before there were some older ones, but I don't mention here now them. And this is the redshift survey for cosmology. Of course, STSS covers an important area in the sky, but then there's Las Campanas redshift survey, 2-degree field galaxy redshift survey, then there is 6-degree field version of it, and several surveys. But it is, when it comes to the spectroscopy and redshift surveys, we are much limited compared to imaging survey. So because for spectroscopy you need more and more time. Of course, there is a way to increase the efficiency of spectroscopic surveys, which is the way of using multi-object spectroscopy. I will talk about that in the second part. So there's a timeline of them. I mean, it's from the Colles review of papers. You can check if you want more. And it started with CFA redshift survey, and it continued with many ones. And STS is a very important part of it. And then, of course, in a given any kind of survey, imaging or spectroscopic, what we are aiming is that we are aiming to increase the number of sources observed or identified or measured, whatever you call, and as a function of the volume. So it is better, of course, the much volume and the much number of objects, and also going the deeper, it's important. Of course, as you increase your volume, the covering area of the sky, of course, in principle, your number of sources will increase. But if you go deeper, if you don't go deeper, it will not that much efficient. So aim is that to go deeper. I mean, in general, ultimate aim is that to go deeper as much as possible and to cover the whole sky. This is the best, but it is not possible so far. So we have to compromise from the depth of the object, I mean the depth of the magnitude, or the area. So for different purposes, people or surveys compromise this between these two, the depth and the area. Here are some important major telescope and their related surveys, because sometimes for a given telescope and instrumentation, many different surveys can be conducted. So it is not one, sometimes there are more. I will go through them quickly. This is, I can skip this. So VIPERS is another spectroscopic survey is performed with the VIMOS spectrograph in the VLT telescope in the two fields of the CFHTLS. So VIPERS can be seen as a spectroscopic follow-up of the CFHTLS survey. And so here, two different surveys, and we can combine the data. So we have a richer data set. In the CFHTLS, we have 5-band imaging data, and then we combine this with the spectroscopic data. So it's a very rich and wealth of information. Then there can be many studies possible. Of course, in the first place, it's cosmic structure, large-scale structures, but still, many things can be possible. So this is actually a nice shape. Also, you can understand this is called pencil beam survey. VIPERS was a pencil beam survey, so they aimed to go deeper, but their field of sky or their footprint was not so large. So in the end, VIPERS can be considered as a pencil beam survey. Again, some completeness limit, but here for the VIPERS and this kind of redshift surveys, completeness limit mostly given as a function of the redshift. So here it is not exactly the magnitudes, but it's more redshifts. So at what redshift range we are complete in the survey. So VIPERS aimed something starting from 0.5 all the way to 1. And even, okay, it goes beyond 1, but it's the main strength is between 0.5 and 1.1, 1.2, something like that. There were other surveys. There are lots of slides here, so I'm just leaving them so you can check. It's just to giving you a kind of historical reference. So there is Vandals again done in the VLT and VIMOS, but I don't go into details. I a little bit speed up. This is the Vandals. Then there's the gamma surveys done in the Anglo-Australian telescope. It's still, it actually is recently completed in the 5 different regions of the sky. They conducted this survey, but mostly the purpose of the gamma is to cover the galaxy groups and galaxy clusters. It's not a general spectroscopic survey. It's mostly focused on one particular topic. But of course, in the meantime, the data allows you to do also some other kind of studies like individual galaxies, kinematical studies, etc. Here, the regions of the gamma. What you can see here is that comparing gamma 2D field SDSS, okay, it's DR9 a little bit older, but in terms of depth, it didn't change so much. And the other 6-degree field surveys. So as you can see, the spectroscopic depth or the redshift limits of the gamma survey is quite higher or quite deeper than SDSS and the others. And again, gamma can be considered as a pencil beam surveys because it's conducted in 5 different regions of the sky, those yellow boxes here. So in the 5 bands, it goes all the way to up to the redshift 0.5. Not so deep, but deeper compared to other existing spectroscopic surveys. Again, here some the wedge diagrams. We call these diagrams when we produce these diagrams when we study to characterize the large-scale structure. So it's just showing you the importance of the gamma data, because before the gamma in that region, we have this kind of spectroscopic redshift, and it's hard to tell to characterize the structure. But after the gamma data accumulated in the years, so we have in the end well-defined structure. But of course, there is no end to that, because here in the lowest redshift regime, we can cover maybe better, but then again, if you go to up to 0.5 or around this redshift range, it is not well covered. So we need more and more deeper data. So there is practically no end to that. Maybe all the way to redshift 2, we will be always looking for deeper data. 2, 2.5, 3. So because you want to characterize the evolution of the structures in the universe. So to do that, to be able to do that, you need to go deeper redshifts. And for spectroscopy, this is not easy, because you need large telescopes or you need extensive or enormous observing time, which is not practical and which is very expensive in terms of telescope operations. So now there will be foremost telescope, which is the predecessor of the VISTA. So VISTA is now transformed to a spectroscopic facility. It is called foremost, and this is an agreement with the ESO. And when the foremost starting the operation, it will conduct many spectroscopic surveys. Of course, some of those surveys will be again dedicated to the galaxy cluster or galaxy redshift surveys. It is as it is mentioned here, because there is an X-ray telescope E-Rosita now still working in the space, and E-Rosita detects lots of galaxy clusters, and those galaxy clusters need to be confirmed or characterized by spectroscopic data. So there's a huge effort behind this to do follow-ups of the E-Rosita sources. So this is the X-ray survey, so imaging spectroscopy. Then I'm just now changing the wavelength regime, but just for one instrument, because I cannot cover all the available or future or the past survey telescopes in the high energies or the other bands, and I'm mostly focused on the optical and infrared, near infrared parts. So E-Rosita is a all-sky X-ray survey. Again, all-sky word is very important, because before the E-Rosita, the previous all-sky X-ray telescope was the ROSAT, which is which is a technology of the 1980s actually. So ROSAT performed a nice job, but with E-Rosita, as it is mentioned here, mostly in the worst case, E-Rosita can be detect sources 30 times deeper than the ROSAT. So it enlarges our X-ray sky. It increases the depth of the X-ray sky. So now we can use those X-ray survey also for cosmological purposes, because now we are detecting distant objects in the X-ray as well. So here, this is another kind of plot, but similar plot in the survey business. Again, this is in the x-axis is the redshift, but this time in the y-axis there is the mass. So this is the mass completeness limit actually as a function of redshift. So here the obstacle is that, or here the tricky part is that it's always easy to detect massive structures like the most massive galaxy clusters or the galaxies, but it's hard to detect the lowest massive ranges. So here it is shown that E-Rosita will be detected almost all massive structures beyond 10 to the 14 and in the redshift range up to 1. Okay, so it's important because before we are not covering this region, so E-Rosita will be covering that, but still it's not enough, because what we are actually again ultimately wanting is that to go even less massive structures. So 10 to the 14 is a good start, but actually if we can enlarge this limit to the 10 to the 13, actually decrease this limit to the 10 to the 13, it is best, because then we can study the lower mass or low mass structures, so we can combine the whole picture of the cosmic evolution together with the because in the hierarchical mass cosmological paradigm, the CDM, lambda CDM paradigm, the most massive structures are formed at last. So in order to characterize their evolution, you need to span an important range of mass to understand how things combine, how things are formed, evolve in the cosmic time. okay, there will be some STSs and foremost together surveys to follow up the E-Rosetta sources. This is one of the STSS surveys called Spiders to detect, to work on the follow up on the E-Rosetta sources. So I just mentioned here, I can skip this. So in many survey, there are, of course, some strategies because there should be science behind it. It's not just covering the sky for just any other purpose. So most of the sciences I mentioned you actually at the beginning, but it's more galactic and extragalactic studies. So some surveys, they categorize these science cases in 4 categories like this: galaxy evolution, galactic archaeology, cosmology, or high energy sky. So there, as you can see, there are many different instruments and telescopes here. Foremost will be used or will be worked together in synergy of this E-Rosetta, Euclid, LSST, Vista, all these instruments mentioned here. This is again the strategy of the HSC. I mentioned about that. It's done in 5 years. It's completed actually, but because of the pandemic, maybe there are some extra nights in these days. But in principle, it's completed. Imaging survey, HSC, and then there will be a spectroscopic survey. It's called PFS, Prime Focus Spectrograph, after the HSC survey. And for instance, here in the PFS case, there are 3 main pillars, as you can see: the cosmology, galactic archaeology, and galaxy evolution. So for the spectroscopic redshift surveys, this is mainly the general picture. Okay, I skipped some of the things. There will be a moon spectrograph for VLT. Is a very highly multiplexed, which I will talk in the second part. I'm checking the time as well. In the second part, so moons is a spectrograph for the VLT. VLT is not a survey telescope. Okay, that's true. But moons is really designed for high field of view and highly multiplex, many number of objects can be observed spectroscopically with the moons at a given time. So even though VLD is not a survey telescope, but together with the moons, it will act as a survey telescope in the practice. So there are many surveys mentioned here, spectroscopic surveys from DESI, RAVE, and some of them are old and completed, some of them are still continue. So here mainly, most of them actually covering the optical wavelength range, as you can see here. But the exception will be the moons, because moons will be conducted in the near infrared passbands. So it will be important because many important spectroscopic survey is being done or have been done in the optical wavelength, but moons will cover the near infrared regime, which is very important for studying high redshift objects, high redshift extragalactic objects. There is also a Sami galaxy survey. This is an interesting survey, but I want to mention this in the second part. But Sami survey is conducted with the AAO telescope, and it is using an integral field spectrograph, which I will mention in the second part. DESI, actually, you remember the dark energy survey project in the southern sky with the Blanca telescope. This is the equivalent, or maybe sister project, let's call, in the dark energy survey. But this time this will be installed in the northern 4-meter telescope in the Arizona, is the Mayal telescope. So the Mayal telescope is going to be transformed to actually already done, and the first test also finished, is already done. They transformed the Mayal telescope to a spectroscopic facility. Again, they converted the prime focus for having able to large field of view. As you can see, is a huge field of view for this kind of telescope, 8 square degree. And they install 5,000 positioner. I will talk that in the second part. And with the help of the 10 spectrograph, they can observe 5,000 objects in a given exposure. So they will cover in the northern sky. They will conduct a spectroscopic experiment. It is called. This is how they call it. Instrument. Okay. So the main target footprint is 14,000 square degree. It is larger than the STSS footprint actually. And this will be completed in a couple of years. I mean, I think it's 5 years. It's, as if I'm not mistaken, it's 5 years is allocated to the telescope, at least in the beginning. So, of course, what is important is that DESI project will enlarge the STSS limits, because STSS also in the same sky, in the more or less the same locations, in the geographical locations as well. But STSS is not going to that much deep, but DESI will be much deeper than the STSS. So we will be studying really deeper structure, and we will be detecting the very high, very distant quasars and some interesting objects in the distant universe. And these are the redshift limits for, because when you are observing, if you are observing quasars or Lyman alpha galaxies or this kind of galaxies, you can go, even with a smaller telescope, you can go much beyond the redshift 1 or 2, because then you detect particular spectroscopic features like Lyman alpha line or H alpha line or different lines. So you can even detect higher redshift objects. But in terms of typical galaxy structures like luminous red galaxies or early this kind of extremely luminous galaxies, you have limitations of different redshift ranges. So it is written here. Okay, I'm just finishing in 2 slides, I guess. And here is some overview of the cosmological redshift surveys. Mostly I'm emphasizing on that, and maybe I am biased because I'm in that working in that topic. But there are other panelists also can contribute. If you have questions, I can also try to answer. And there are some current surveys, as I mentioned some of them already. And DESI started actually its operations. Euclid will be a space project and will be starting here. It's 2022, but actually since 2017 it's delayed. So I'm not sure if it is certain this time. And there will be a infrared all-sky survey I didn't mention here, which is called Roman Space Telescope. Actually, it's previously known as the V1st satellite. And this is expected even beyond 2026, maybe 28, 29, something like that. So Roman Space Telescope will be conducting a infrared, not just near infrared, mid-infrared, and far infrared sky survey, whole sky survey. So we didn't have such a telescope. There was the VICE, but all the other infrared telescopes and infrared space telescopes, they are not targeted for the whole sky. So Roman will be targeting whole infrared sky. It will be very important input for our data sets. Okay, this is just an again overview of slide to show you why we are doing deep galaxy surveys, why we need them. There are 3 different purposes again: characterizing the large-scale structure or the distribution of the large-scale structure, and some mass and luminosity evolution of the galaxies, and categorizing galaxies and making classifications and understanding their interaction or their together the properties of those galaxies. So to be able to do that, you need a large and rich data set, which requires spectroscopy. Just with imaging data, you cannot do all these studies, especially large-scale structures. You cannot do with imaging data. You need spectroscopic data. The 2 latter target purposes, maybe you can cover at a limit with some limitations, of course, in the imaging data, photometric data, I mean. But for a whole census of those studies, you need imaging plus spectroscopic data, which is now we are completing the second part, because imaging part is we have very rich data sets from many telescopes. I mentioned some of them, some major of them, with the spectroscopic ones starting these days actually. So here I will stop with that. I will give a break with this one, a short break, by the way. And this is the ground-based and space telescopes, what we can do. Of course, James Webb will be covering a large redshift range and go deeper. But James Webb is not a survey telescope, but of course it will help. It will conduct some maybe pencil beam surveys, but not large sky survey. LSST conducting from the optical, so it doesn't go so deep. Then there will be extremely large telescopes like Giant Magellan Telescope, European extremely large telescope. There will be 30-meter telescope. Those giant telescopes will be, of course, covering deeper because of their giant mirrors. But then there is the Nancy Roman Space Telescope. This is the mentioned here as V first, but it's the Roman. So with the infrared, you can go really much deeper. There will be Euclid. There is ALMA already in operation. And this is the epochs we are covering. So we need a future radio survey to cover the really first galaxies and the dark ages of the universe to understand what's happening there, because of the redshift, all the photons are redshifted coming from those parts of the universe, redshifted towards the longer wavelengths. So they are beyond the infrared wavelength. So to be able to cover the dark part of the universe, dark times of the universe, dark ages of the universe, you need to go radio wavelengths. This is the future radio sky, future radio astronomy. So I stop here for 3-5 minutes for a short break, then I will continue if you are not tired.
Thanks a lot.
There are
Sinan.
some.
May I ask a question?
Sure,
Thank you.
I can.
Okay, so maybe it's a naive question. Because I'm not an observer, so
Okay.
how do you decide whether you said you are observing dark matter, right?
You detect, yes, but it's not.
How do you detect that dark matter?
Okay,
Do you know
detect,
what that is?
Yeah, sure. You do this detection indirectly. So in the observation astronomy, there is no direct way except the weak lensing. So if you do the weak lensing studies, you can characterize the dark matter, mass of dark matter, of course. I am not talking about the particles and the nature of the dark matter. I'm talking here the mass of the dark matter.
I understand. I wanted to be sure. That's it.
Okay.
I have the same opinion. So when does this dark age ended?
I mean, it started with the CMB. So before the CMB.
Okay, but I have the number about 200 million years.
This kind of definitions can really change. So there is no strict and sharp definition. This is except the CMB, because we are covering this region. So maybe in the theoretical part and in the simulation part, you can speak more certain. But from the observational point of view, we are still exploring. So we don't know.
But there is a paper in Nature, Bosman et al. They talk about the shifting of the 21 centimeter line.
Okay.
In radio observation, something like 78 megahertz or so.
Okay.
And then they're saying that actually something like 180 million years after recombination.
Okay, I haven't seen that paper. It can be, but still it's much beyond our limit now. So
how far can you? But the James Webb can go there.
Sorry, I don't understand.
The James Webb telescope.
Yeah, with the infrared, you cannot reach that. Maybe within the array of the dark ages, but you cannot reach all the way because you need to go to the radio to detect the neutral hydrogen or neutral elements. So you need to go there. It's very cold, so there is no classical way of emissions. I mean, so you need to go to the radio.
Okay, but then the dark age era, the dark age epoch, is infrared, right?
No, it's just a general nomenclature. Is to define that we don't have so much photon there, so it is beyond the infrared. That's why it's called dark ages. We cannot see them. We don't not so many photons reaching us.
But
and
there is reionization by the first star. Cynthia Saad will talk about it.
Okay.
There is the first star,
Yeah.
reionized the universe.
Yes. It is.
And they
Yeah.
end their
Okay.
dark age.
Okay. Okay, that's true.
I see. Okay, so I just wanted
There's
to
no
know
problem.
because this is a matter of initial condition when the dark age ends.
Maybe there's
Mauricio, we couldn't hear you.
No, I just say that you have to consider that the photons coming from the first stars are red shifted. So you have to consider longer
wavelengths. Yeah.
Okay.
I have to go up to let's say 10 or so in redshift, at least.
Yeah.
This is pre-galactic.
May I ask a question on more nearby stuff? Your discussion made clear that the James Webb Telescope will clarify things in the infrared, but it will not provide tools to measure abundances in ultraviolet. Many crucial elements and even their isotopes, I'm thinking of lead, lead-208 in particular, have been observed. What we know has been observed thanks to the Hubble Space Telescope.
Yeah.
And I'm wondering, do we have in the future possibilities of new facilities doing that, doing measurements in the ultraviolet light for abundances like the Hubble Space Telescope? Thank you.
Thank you. Actually, the survey telescope Galaxy, you probably performed in the whole sky. But then recently there are some projects under development, especially CubeSat projects. There are very ambitious CubeSat projects for covering the UV surveys. I'm following some of them, but for the moment I don't remember their name. But it's mainly US based. If you search UV survey and CubeSat in the internet, you will find them. So they are really doing to enlarge this study. Actually, maybe also maybe you followed, so I don't know, but recently these things already, something related to that also discussed in the IAU General Assembly. So they wanted to set the standards for the UV astronomy, UV band passes for the future surveys. So recently a resolution also passed about that. So as far as I know, I can say that there are some CubeSat projects for the UV astronomy, but not larger facility to my knowledge.
Oh, yeah. No, I guess you are right. It's not only your knowledge. I guess at least our American colleagues working in nuclear astrophysics from the observational point of view have not been very pleased by the future.
Could be, yeah, could be. Thank you. So
okay, we didn't see any questions meanwhile. So
I can't. Okay, they don't put questions in Slack, right? Because I cannot follow.
Not so far.
Okay, not so far.
it's good to see that the number is rising. It's
Really?
45 attendees right now.
We started like 40 or something.
Started 29 to 45. Good.
But actually the registered participants are much more than that, right?
100, yes.
100, okay. Oh.
Well, everybody has actually some time difference, so maybe some of them are not going to be able to attend live, so they are asking for recordings. We are right now recording every lecture, and it's recording on the cloud servers. Maybe later, after the permissions have been reached, we will be able to share them with the participants. I don't know right now just exactly when.
Okay.
So the students don't like asking questions anywhere.
Then, yeah, that's possible, yes.
In this type of webinar series, it's not able to see them, see their faces, but maybe the afternoon session and the social time and the informal break, actually, they will be able to talk to each other face to face as well.
And in any case, I guess some difficulty at the beginning is normal, but you have provided very useful tools. So students are invited to call us by email, by chat, or by any means, even outside the sessions, of course, in due time, but we shall answer.
Yeah, we'll try to evoke them.
Yes. Okay.
So I have time until 2:10, right? There is another something behind after me.
No, after your presentation, we have a 1 hour break, so you're free actually.
Okay.
So
maybe
there is actually a question now.
I have one. What are the
best ways?
Wow, I don't know. It's a very generic. I mean, I know it's a very broad question, but data reduction, of course, but if I understand your question correct, the best way is to use pipelines, of course, because with the survey data, you cannot do individual studies. And first of all, it has to be homogenized data. So there should be some pipelines dedicated to that data, and people actually doing that. I mean, because they know the data structure, they know the instruments, they develop special tools and pipelines. And then afterwards, they provide actually even reduced and analyzed data for you. But of course, you can always request and sometimes request and get the raw data. But nowadays, I think is the lazy part of the astronomy, because everybody goes to the surveys, and from the databases, you can just extract the information. For instance, in the STSS, you don't need to care about the spectroscopic reduction. But if you pay attention, in many cases, in the pipeline of STSS really fails, because you see some bad estimates of the redshift of, it's not perfect. So you need to be careful about that. But of course, it gives you a big advantage, because you can really work with enormous number of objects in a given time, shortly, right away, without any big effort. But you need to be careful when you are playing with your data. I don't know if it is enough. By the way, I can start if you are okay, because I'm...
Okay, let's start the second part of the lecture.
Okay.
Thanks for the question.
I'm scaring with the length of my second part, but I can again skip shortly. Maybe I can extend some time, 10 minutes, if you allow me.
Sure.
Let's see. Okay.
Okay.
So, I didn't share, right? Where's my Zoom window? Share screen again. Okay. So I give the title as this: Spectroscopic Instrumentation in Astronomy. Here, this is the basic spectrograph structure. This is a prism spectrograph. Of course, it is shown here, but it doesn't matter. We need a disperser. Why this thing doesn't go? Okay, anyway. So this is the disperser. In the very old time, it was the prism. Then later on, we started to use many other different optical elements for the dispersing the light. But this is the very broad and rough and generic spectroscopic design. So why I'm emphasizing this? Because there is one slit, and we are just observing dispersing the light coming from the slit. So with slit, we can limit the photons where they are coming from. So we can limit the objects. And of course, we are using the diffraction theory here and with the slit, so we can have an extraction of the wavelength in the end. And here the problem is that I told you already that we want to observe many objects, either it's star or galaxy, doesn't matter, but in different surveys, the aim is always having larger samples of objects, because in the surveys, like our friend asked a question, in the survey, you need to really reduce and study many objects, because if you don't increase your sample, you cannot do statistical studies. Surveys are not designed for individual studies or just for one object. So as a result of that, we need to find another way to observing, because with this kind of spectrograph, each time we can observe only one object, and it is not efficient. We cannot do that. So, but before coming to that, let me again give you just some lines of information. So this is the main generically important topics covered in the spectroscopic survey, and there are some already instruments mentioned. I also mentioned them. So what we started to do, that we started to place more than one slit in the focal plane. So if you place many slits in the focal plane together, so it means that we can get spectra of many objects in a given exposure in one time. Okay, so then we are limited with the field of view of the CCD camera. So we can put slits, of course, but in this example, slits are here, these short dashes. So in this, because dispersion axis is the vertical, is opposite, orthogonal to these things, this dash. So as a result, I can only cover some maybe 15 or 20 spectra in this field of view. I cannot put more than that, but it is not enough. But it's a starting point, but it's not enough. So this is just a real example. So again, there are some marked object here in the sky, in the image, in this image, and this is the spectra. So spectra are vertical lines, actually individual spectra. So this is called multi-object spectroscopy, but using with a slit mask. Okay, so this is the mask. This is some different materials can be used, but this is just any material, let's say, at the moment. Details are not important. And this material is, you punch the slits, and this is of course you need to know the precise location of your objects, and then you place this mask into the instrument or spectrograph, and then you get spectra of all these objects at the same time. As you can see, there are several objects, but it is not enough for what I described to you in the first part. So then there will be some other kind of multi-object spectroscopy methods, MOS. I will call MOS. So this one of those things are fiber fed spectrograph. So we create a huge plates, like in the case of STSS. This is the STSS actually. In the case of STSS, you put you design a big plate, and you put fibers in places, and then all these fibers are transferring the light to the spectrograph. Why we need that? Because in the previous example, spectrograph already attached to the telescope, and we put a mask. Actually, this kind of mask are very smaller things, like in my hand size, and we put this kind of mask into the spectrograph, and spectrograph is attached to the telescope. But if you want to enlarge the field of view with many objects at a given time, for instance, in the case of STSS, there are 640 objects at a given time. So it's a huge. So we cannot install a huge spectrograph to the telescope. I mean, of course we can do that, but we don't want that, because if we attach this kind of huge instrument, this is not good for the dynamical or the stability of the telescope. So instead, what we do, we put the spectrograph aside in the dome somewhere, doesn't matter, but not attached to the telescope in many cases. And we move or we transfer the light using the fibers. So this is this kind of thing called fiber-fed spectrographs, and this is actually currently the most important or most spreadly used spectrograph design, fiber-fed spectrographs. Okay, and the advantage of this fiber-fed spectrograph, since you have the fiber, you can direct these fibers on the certain position on the CCD. So it is not randomly located, or it is not, just their location on the sky. You get the light and you direct to whatever or wherever you want. So in the case of that, the efficiency of the CCD area is increased because now we put things in order, and as a result, we have maybe 50 spectra in a given exposure compared to most masks. Okay, so now we improved the number of the objects. So we observe maybe 50 objects in one time. Okay, but still not enough. And this is the case of SDSS because of course there's always advantages and disadvantages, because in this case the disadvantage is that you need to design these big plates and you need to install the fibers, to put the fibers by hand, because there's no machine doing that. So in the case of SDSS, there are technicians doing that, and they are putting all 600 fibers from before each observing. Actually, they can do that 2 times in a night, not many, but it's already something and also enough. But this is a huge effort, and there's a human effort behind that. And we need to speed up this process as well. And this is the case of SDSS. Again, this is the fibers attaching to the fiber plate, and this plate is in the focal plane of the instrument, but not the spectrograph. The spectrograph is somewhere else. So we are carrying the light together, these fibers, cables, to somewhere else than the telescope. Maybe in the same, dome level, maybe somewhere near the dome, or maybe somewhere spatial allocated place. I don't know. It doesn't matter. So now people are, especially for big surveys, everything should be robotized and automatized. To be able to automatize this process, robotic arms developed, especially in the Anglo-Western Observatory. This is where I borrowed the slides. In the Anglo-Western Observatory is the pioneer in this field, and they developed lots of multi-object spectroscopical tools and machines for that. So this robot designs these fibers for you. So you don't do them by hand. Instead, you design on the computer with the software, and then you send the commands, and this robot's arm, actually, it's like sewing, or maybe the most sensible similarity is that how the spider produces form is web. It is web. This machine producing a web of slits, and it takes some time, of course, but it is automatized. It is robotized. It's very important. But here, as you can see, another view of these things. And this robotic arm really, it's like the spider creating this web of slits, but it's not so efficient in terms of time, because roughly it takes 1 hour to complete this design. So just imagine if you realize that you make a mirror, you make an error or mistake in the design, or you just change your mind and you want to observe another objects in the same field of view. So it will take another 1 hour to redesign and to be ready to observe with the telescope. So this is a very good thing, automatized, but it is a bit slow. So now we have more and more different things. These are all examples. So examples are here in the right part. So this is the detector instrument. So in this case, this is 2-degree field. In this case, this is OSPOS. And this is the type of the fiber positioner. In this case, it's called pick and place. This robotic arm pick the fiber and go and bring it to the actual position, or the position that you desire, and you put it there. So it is called pick and place fiber positioners. Okay. So I skipped those things, and there are many spectrograph instruments and different observatories, different telescopes using this kind of instruments, pick and place. This is the view again, like this. But then again, because of the design time and redesigning time, people again wanted to develop a new tool to improve the efficiency. So in this tool is called theta phi positioners. Theta phi positioners are constant, so they are already in the focal plane. Their locations doesn't change, but they can rotate in their axis, and they have also another part here. This part is also located. So first, theta, that's why it is called theta phi. So it's there are two angles. So there can be two different rotations, and there are, of course, many combinations of them. So the main pillar, main tool is that they combine, rotate in its axis, and then they have another arm. It can also rotate. So of course, it gives some limitations in terms of the area, because you cannot maybe locate these objects for every position in the sky. But with different telescope positionings, you can get over this obstacle. But the good part is that it is very fast, because you don't need to wait all this pick and place robotic arms. These things are easily and quickly rotate and you can make the positions. So there are many spectroscopic instruments. Survey is using theta phi positioners, and this is the upside view, and this is the view you don't understand maybe here in this view, but here, as you can see, there are 5,000 or 4,000 many objects, many theta phi positioners here in the case of LEMOST, and you observe a large field of view robotically doing that. And this is the Grand Tecan in the Canary Islands, and it's also Megara is also using theta phi, and this is the same kind of objects. So actually, there are fibers in the core, and this fiber main position is constant, but it can rotate and it can have some arm. I will show another way of it, but I think you get the idea. So DESI will also use theta phi positioners, but in the case of DESI, since they are putting this positioning system in the prime focus, so it's a huge prime focus. You remember in the imaging, it was 8 square degree. And now it's a huge prime focus, and there can be 5,000 of positions that can be located. But then the problem is that you cannot use one single spectrograph to feed all these 5,000 positioners. So what they did, they divided this focal plane in 10 different spectrographs, and they call these petals. So this triangle shaped thing, the slices. So each petal contains like 500 theta phi positioner. In the total, they have 5,000, but each petal is directed to another spectrograph. But this is unique spectrograph. They are very same, typical unique spectrograph, but they have 10 spectrographs in this project. So you can imagine, you can understand, I think, the capacity of the project. Then in the Sloan 5, also they are now transiting to the theta phi positioners, because I just mentioned that up to now in the Sloan spectroscopic surveys, there is always a manpower needed for placing the fibers, and now they are changing now they are also changing the system as well. I mentioned moon spectrograph. They are also using the theta phi positioner, so I maybe should. Okay, I just 1 minute here. Some people, okay, this is a huge. Maybe when you compare from the mask, slit mask, it's a huge development, and you can think that, okay, this is the ultimate solution for multi-object spectroscopy, but still not, because some people still are not happy. Astronomers are always desiring more and more. So they are not happy because of this rotation, and there are some limitations of this, because you cannot rotate. You have to rotate as a coordinately coherent way of all the theta pi positioners, because sometimes they are overlapping, and there are some always dead zones between this positioners. So there are some regions that you cannot cover. So what can be the solution is that if we can use a thinner and most effective way, and this is called tilting spines, and this is also a recent study. And in the tilting spines, there is no theta phi kind positioners, but spines can be tilted differently, so it can increase the space density. I mean the survey density. It's called petrel zone. You can increase that thing. And this is a recent, let's say, technologies on the test bed now. But soon we will see instrument with the tilting spines. In the ESOP, AAO is now developing a spectrograph for the Formos consortium, but it's not completed yet. I skip a little bit. Okay, the other one is I like a lot, I mean, personally, this thing is called Starbucks. Starbucks are placed on a glass plate, and using with the magnetic or electrical voltage, they are positioned on the glass plate easily, and you put them separately. But of course, Starbucks cannot be highly multiplexing. The term multiplexing means that how many objects we can get spectrum. Okay, it's called multiplexing. So in the Starbucks, the multiplexing is not so high compared to theta phi positioners or tilted spines, etc. But it's more efficient because easily and very fast, in a very fast way, you can move these fibers, and they don't overlap. It's not so much complicated in terms of design, but you are limited with the number. So it's a compromise. Some people can prefer this thing. So there are many spectrograph is being built or already in operation using Starbuck positioner. So all I'm talking here is the fiber positioning, because in the multi-object spectroscopy, this is the key point, is the fiber positioning, because you need to put the fibers in the for the targets. Targets can be stars, targets can be galaxies, etc. But here the idea is always that the fiber from the fiber positioner, it is in the focal plane. You get the light, you carry the light through the fibers, and these cables can be any longer depending on your physical limitations. And of course, there's a spectrograph somewhere. So this is the way. But of course, there's some technical things important, especially when you are getting the fiber from the focal plane, and when you are feeding the spectrograph, the fibers should be really as vertical or as directed as much possible. And here there are some important boxes can handle this kind of alignment, because otherwise cable can be bended many times on the way to reach the spectrograph, but at the entrance and exit pupils, the fibers should be vertical. Okay, then you may ask that what happens in the space? And in the space, all these technical things can be used in principle, but you don't want them, because all these technical things can create some complexity, and space you cannot handle. You cannot do maintenance operations. For instance, for the JWST space telescope, there is a spectral instrument called NIRSPEC, and in the NIRSPEC there is a MOS mode, multi-object spectroscopy, but not using any of the fiber positioning, because all these positioners can create a complexity and can create some malfunction, and in space you cannot tolerate for that. So what do you do? Instead of, you can use MOEMs shortly. It's called multi-object electromechanical mirrors. So these mirrors are very small. So imagine that on the CCD surface, you put a grid of shutters, but very small shutters. So in this case, shutters plays like a slit or the fibers, okay? Of course, they are a rectangular shape in this case, and they are as small as possible. But then you open those shutters or not, depending on your target. If you have a target in the line of sight, in the depth corresponding to the shutter, you open the shutter, so you expose it or you don't. So here it is less complicated in terms of mechanical design, and it is selected for the JWST and maybe some other instruments. So here also there are two things actually. First, we have the shutters, but also there is a reflecting surface actually behind the shutters, and based on the angles, you can separate the spectra, so the spectra are not overlapped on the CCD field of view. So because for dispersing, you need to kind of dispersing element. This is the reflective surface, like the grism in the typical spectrographs. So this reflective surface will act as a disperser, and then we will have the spectra. But since we don't want that all the spectra overlap, so we arrange those micro shutters accordingly to separate the spectra to prevent any overlaps. Okay, so in the next let me stop here. First, what we are doing is that in the survey astronomy, now we are in the era, I'm just again emphasizing this, we are now in the era of spectroscopic surveys. Okay, so many facilities are now being developed, installed, or assembled, etc. Also, some of them are in the design process in these days. So what we can do so far in STSS, we have 1 billion objects. I mentioned these numbers already. We have 1 billion and more objects actually from imaging, but we have only 5 million objects with spectra. So it's 5, as you see, 0.5%. In the DESI is a slightly larger telescope, 4 meter, 2 billion objects from imaging, and they plan 40 million objects with spectra. It's 2%. As you can see, there's an important increase compared to STSS, but still, DESI is a spectroscopic instrument designed for that. But still, they can only observe 2% of the imaging the sources that they have detected from the imaging. So it's not complete. Rubin LSST is not a spectroscopic survey, so the LSST provide many sources to be followed for the spectroscopy. But then, who will do this spectroscopy? Who will observe these numbers of objects spectroscopically? As you can see, STSS could observe 5 million. DESI will observe 40 million, but with LSST, we will need to observe these numbers of objects with spectroscopically. So how we can manage? In the meantime, the number of spectroscopy, the multiplexing numbers are increased. There is a typical something similar to Moore's law in the electronics. You may the economy, but also in electronics, you may know. So with every 10 years, or we are doubling the number of objects with redshifts. Of course, I'm now talking about redshifts. So we started with CFA redshift survey, like 1,000 objects, then it increased to hundreds of thousands of objects. With STSS, we are reached to millions of objects. With DESI is a 40 million, but then what will next? We need more and more objects. There's a project called Mega Mapper, but it's just a phase A project, the design project for the United States, for NASA. So it is not certain it will be reality or not, but there's a huge spectroscopic facility is considered. So how those facilities with multiplexing numbers more than 1,000 located in the Earth, as you can see, there are DESI, STSS, VLT have MOONS and FORMOST. There are VIV in the Canary Islands, and there's LAMOST, there's Subaru PSF, and there are some red instruments. They are in design, in development, or in just discussion now. For instance, MSC is in design, in the development process. KEC-Phobos is again development process, but Mega Mapper is not certain. We don't know it will be reality. Spectres, SSST also, we don't know those things. So I will mention. So the most realistic ones, here the list of the realistic current and some future facilities. And VIV is not started yet, FORMOS not started yet, DESI just started, MOONS not started yet, PFS not started yet. So many of those instruments, multi-object spectroscopy, they are not started yet, and soon we are expecting them to be operation. But then there is a special one highlighted here as blue, is the 10-meter class, but actually is a 11.2 meter telescope. It's called Mauna Kea Spectroscopic Explorer. It will be a spectroscopy machine, a huge machine located in the Mauna Kea instead of the CFHT. So they will transform the CFHT telescope, the dome, to a spectroscopic facility, which is called MSE in short. Again, here the multiplexing number together with the size of the telescopes. As you can see, actually, normally you can increase the multiplexing number with the smaller telescope because of the field of view limitations. But what may be interesting is MegaMapper and this kind of projects is the size of the telescope and also increasing the multiplexing number. So MSC actually, the other ones are just prototypes and design projects, so we are not certain about them, but MSC is under development. So MSC actually will be the really new standard for the spectroscopic survey. So, I mean, I can really easily say that what STSS did for the imaging astronomy, imaging survey, MSE will do that the same for the spectroscopic survey soon. So here again, another kind of plot, I mean, diagram. In nowadays, I mean, today, what we have in terms of multiplexing, and in the soon we will have these numbers of objects for spectroscopy. So there are different contribution coming from different telescope and instruments is located here with the different colors. But what you understand is that soon in the next 10 years, in the next decade, let's say, in the next decade, we will really multiply the number of spectra really significantly. Foremost is already mentioned that is the VISTA telescope will be transformed to a spectroscopic machine. I will go very, let me check. Okay, I will go very quickly this. So those technical details I don't read, so you can have them later. I just want to emphasize again the science topics now and what kind of science topics can be done or can be studied with this kind of spectroscopic facilities. Of course, cosmology, galaxy evolution, high energy follow-ups like E Rosetta follow-ups or any kind of high energy follow-ups, or galactic studies or AGNs and this kind of studies. There are some examples here predicted or foreseen with this kind of instruments. There are different PI, different people are leading these projects. So with the wealth of information, with the wealth of spectroscopy, actually, what we can do the contribution from the dwarf galaxies to our own galaxy. So it's the Sagittarius dwarf galaxy was discovered in 1994 in a similar way in terms of by studying the metallicity increasing in the halo. So with a similar fashion, we can study spectroscopically in the galactic halo, the stars, and then we can maybe detect and identify this kind of orbits of the dwarf galaxies, so where they moved, where they passed through from our galaxy, so we can characterize this kind of contamination. Of course, I already mentioned gamma. So of course, the structure of the large-scale structure is always on the topic, on the table is always when it comes to the spectroscopy. So this is the moon spectrograph. Again, the details I skip. I leave it for you. This is a huge instrument, by the way. Will be located in the Nasmyth platform of the VLT telescope, and this is again the theta 5 positioners I already mentioned. This is a nice way of showing you how theta 5 positioners can move on the focal plane. So how you can create different combinations of design of the target design. And this is the nice way. I already mentioned this, so I skip. So here in the moon survey, there are some GTO science behind that. So what does it mean? Guaranteed time of observation. So when people are, especially big consortiums, when they are developing instruments for observatories or telescopes, like in the case of ESO and VLT, and the consortium also demand some time. So this is called GTO time. And so the ESO guaranteed some time to the instrument developers. So instrument developers will conduct their own research, but it is not one or two persons. There's hundreds of persons behind that, people behind that. So it's a large consortium behind the moon spectrograph, and this is their working groups. So they want to work on these topics. So details are in this messenger. You can read if you want. Again, what kind of diagnostic can be used in the spectroscopy? there are different things we can measure: the metallicity, star formation rate. We can define the stellar population, etc. So all this diagnostics or observables we can use to define. We can study the objects. There is Keck and Phobos. I'm a bit skipping now because it's repeating similar things, so I don't need to emphasize all at each time. But there are different spectrograph. I'm just here now. Why I'm putting the slides again here. This time I'm just emphasizing the scientific aims or targets of those telescopes. Of course, they are not same, but there's a big overlap in this kind of projects. There are big overlap of galactic archaeology and extragalactic studies, but there can be some details or differences between from survey to survey. And in this case, I'm just showing you to have an idea, to have a flavor of what can be done with this kind of instruments. I skip this. Again, the DESI, I already mentioned the spectrograph, these petals, I mentioned about already them, these theta 5 positioners. So I skip those things. And this is the MSc I mentioned. It's, I think, one of the most important spectroscopic instrument and projects in the nowadays and the currently existing. So they are transforming CFHT to MSc. And there's a reason behind that, but I don't want to spend my time. Maybe in the discussion we can think why they are transforming this. I can tell you that. So this is the largest size possible or feasible to put inside the dome is the 11-meter telescope. So they removed the 4-meter, 3.6 meter CFHT telescope, put a 11-meter telescope inside, of course with a different, with a compact, more compact design. And they can use the fiber positioner will be more than 3,000. So MSc will observe objects, 3,000 objects at the same time. But this time something is different because VLT or the other DESI, Mayal telescope, all the other telescope, they were smaller telescope. This time we have an 11-meter telescope, which means that we will spend shorter time, shorter exposure times, or we can go easily deeper in terms of spectroscopy compared to all the other projects that I mentioned. Here, the capability of the MSc, of course, there's also one additional capability of MSc compared to others is the infrared part. Like the moon spectrographs, MSc also will cover some infrared bands, infrared spectroscopy, near infrared spectroscopy, of course. So it will be important. So this is the last line, I think, is the summary of what I wanted to say. Okay. Again, what can be done in the MSc? Of course, the chemical composition of exoplanets or very compact galaxies, quasar absorption spectroscopy, or intergalactic medium to study the intergalactic medium in the line of sight. And of course, lots of exact surveys and galactic archaeology, I don't mention at all because it's already there. This is one more thing about that. Mosaic is a camera, is a spectroscopic detector called, but it's for the EELT, is a 34-meter large, gigantic ISO telescope. It will be the largest telescope in the ground, on the ground. So Mosaic is a multi-object spectroscopic instrument designed for the EELT. And this is the science topic of the Mosaic and what they wanted to do. Of course, you can go really deep to these redshift ranges because it's a telescope is huge itself. I already showed this, so I skipped that. Okay, a few more slides and I will finish. Here, ESO conducted recently a survey to the community. Of course, it's the European community in this case, but it's representative of the whole international astronomical community, I think. And in the case of the ESO community, people are demanded mostly a dedicated optical and infrared spectroscopic 10+ meter telescope. So it's the MSE actually, but MSE is a French-Canadian based project Of course, okay, it's a European involved, but not the ISO itself involved. So it will not be open to the whole European community, but maybe it can change later. So ISO community will require or demand a large telescope, more than 10 meter size, but dedicated telescope is actually they are defining the MSE telescope actually. So as you can see, based on this survey, people really requesting and survey telescope, large survey and spectroscopic telescope. And this is the currently multi-object spectroscopic window. It's a nice plot. You may spend some time later. So this is the wavelength ranges that we can cover, and this is the multiplexing number again. So this is what is available at the ISO, only at the ISO. So it's not all the international. This is again the ISO plot. So this is the multi-object spectrographs available at the ISO. There will be mosaic later for the 39 meter, and these are already available except the foremost and the moons. All these are in operation already and very old. Some of them are very old. And okay, here I will stop with that. Here, you may ask that how we can decide what to observe. Okay, so to be able to decide what to observe, of course, there should be some imaging survey previously has been done or performed. So there should be some decision mechanisms based on your science cases. So galactic sciences or extragalactic sciences can change the topic and can change your strategy. So there should be some really data flow, or there should be some pipeline behind that to even for designing. Okay, because after you design your survey, then you automatize everything and the telescope will start operation and the instrument will start its operations. But then reducing the data will be also different than for a star, than for a galaxy. So all these things should be in coordination and in a sort of supervised way, in the high level supervised way. And this is not so easy in the case of large spectroscopic surveys. So this is a space where the big data, where the data analysts, software developers, and all these people are very important, crucial in the operation of this thing. So again, our friend has asked before the break, what is the best way? Best way is to use pipelines. So, but you need some specialized and expert people to develop these pipelines. Most of the cases, astronomers can develop by themselves some software, some codes for plotting, analyzing, some tools we can handle by ourselves for individual study. But for surveys, we cannot do that. So there should be some dedicated people to take care of all this complicated data structure, pipeline structure, etc. So thank you for your patience and interest. I stop here. If you have more questions, we can discuss.
Thanks, Sinan. Let me see.
Chat. Okay, I open the chat here. Maybe many people in the Western Europe, they are waiting to going to lunch. So they may be hungry and tired already.
Yeah, we have a 1 hour break right now after the session.
Well,
So,
can I say something, Ayşegül?
sure.
Hello, Mr. Han.
Hello, Sinan. Welcome. Not to ask questions, Sinan, but to share an information. Sinan is the General Secretary of Turkish Astronomical Society. And we would like to thank Turkish Astronomical Society and Sinan for sponsoring this meeting.
Thank you. Thank you. We are really
thank you.
Thank
Happy
you,
again.
to be part of it. Yeah.
Yes.
Well, Sinan is also part of the new telescope coming to Turkey. coming,
Doug.
as I say, it is the Eastern Anatolian Observatory, which he will be also introducing on Wednesday morning.
Yeah, together with Süleyman, we will providing nice images and videos for you. I hope you will be.
Yeah, but Wednesday is also an important day for the Eastern Anatolian Observatory because what was the situation, Sinan?
Okay, the Wednesday, the mirror is coming from Russia. So mirror is coated and tested and everything is okay. Now it's packed. So Wednesday, I will check the time. I will tell you later, but Wednesday, the mirror is arriving to Turkey. And if the weather will be okay, it will be immediately taken to the top, to the site. If the weather and road is not good, so it will be stored somewhere in the university. So it is one of the fragile moments of the project because mirror is the everything.
Yeah, we are also excited about this project.
Yeah.
It's not that a big the telescope, as you were mentioning in these projects.
Yeah.
But it will mean something because it will be also working in an infrared for us.
Yeah.
Also in this geography.
I have a curiosity.
Sure.
So I apologize for this. I don't work in astronomical technologies since more than 20 years, but once upon a time I remember that Russian mirrors were exceptionally good from the optical point of view, but very heavy. Is this so even now?
Yeah, in a way that's true. And so the main mirror production is done actually in Germany by the Schott, very famous Schott company. And the other main producer of the mirror is the actually United States, the National Observatory, the Stewart Laboratory in Arizona. And basically they produces the mirror because now we don't have the glass mirrors, as you may know. We are using different and lightweight materials. So this is a big advantage, but there are also some complication related to those kind of materials. But still, there is one thing that Russia leads in the business, of course, besides the United States, the coating. So Russia is not producing the mirror blanks. Of course, for their purposes, for themselves, they do, but they are not a big company or the big competitor in the business. But many people are sending their mirrors for coating to Russia. As we did.
It's gold coating or aluminum coating?
Yeah, different. It depends on your material, but it doesn't matter because the coating plant can be used for many metals. But basically, aluminium, typically in the aluminium or maybe combination of silver.
Yours will be aluminium.
But there is it's a mixed because there's a kind of because we want to increase the infrared reflectivity.
Yeah, exactly. That was my point. Gold is good for infrared.
Yeah, but it's expensive and maybe it's then dangerous for ground-based telescopes. Some people can try to, I don't know, steal the. In the space projects, always gold is used for the mirrors. Because also for the degradation because of the high energy particles. But in the ground-based, they are using some kind of mixture of silver, aluminium, and some materials to increase the reflectivity.
Thank you.
You're welcome.
Gold is an R process. So we need more neutron-star mergers or supernovae to produce it.
Yeah, that's true.
It's a rare element.
So,
okay,
do we have any questions, students?
They are silent, quite.
We'll wake them up later.
I'm also wondering what is the fraction of Turkish students participating? I mean, now, but attending, not the registered, but.
Now attending.
Yeah, maybe. I see more international actually. It's
more international than Turkish. It's
interesting.
Okay. Okay, I guess we don't have at the moment. Yeah, you are going to say something?
Me? No.
Okay.
No.
So, this is the end of our second session. We're going to have 1 hour break for most Central European people who are going to have a lunch, and the others are going to have a coffee or something. And we're going to get back here in an hour, and so that we'll be continuing with the end of the Dark Ages. We'll see who ended the Dark Ages after the Big Bang, the first stars, and so on, the nucleosynthesis for the first stars, and so on. And we will continue with two consecutive talks in an hour.
So it will be 12:30 UTC.
Yes, exactly.
Okay, thank you very much. Have a good lunch, everyone.
Okay, ciao everyone.
Ciao, ciao.
So see you in an hour.
It's a bit early for Spain, but
you're
ciao,
right.
ciao.
Hasta la vista, Ilma.
Hasta pronto.
Hasta pronto. Ciao.
Ciao. Ciao, ciao. Ciao.
Ciao, see you.